On October 21st, 2025, something happened that had never occurred before in the history of planetary defense. The International Asteroid Warning Network, a United Nations-backed system designed to protect Earth from cosmic impacts, activated an observation campaign for an object that poses absolutely zero threat to our planet. Not an asteroid on a collision course, not a comet threatening impact, an interstellar visitor that will never come closer than 270 million kilometers to Earth, already moving away from us, not toward us. So here's the question we need to ask. Why would astronomers worldwide mobilize planetary defense protocols for something that isn't defending us from anything? This isn't speculation. This isn't conspiracy theory. This is documented, verifiable activation of international scientific resources on a scale we've never seen before, targeting an object with characteristics that don't match any comet in our databases, and it's happening right now, in real time, during a 2-month window that represents humanity's only chance to study this visitor before it vanishes into interstellar space forever. The object is called 3I/Atlas, the third confirmed interstellar object ever detected passing through our solar system. And on July 1st, 2025, when the Atlas Survey Telescope in Chile first spotted it, nobody could have predicted what would unfold over the following months. A cascade of observations revealing chemical signatures that shouldn't exist, a trajectory aligned with mathematical precision to the plane of our planetary system. Behavior that defies our understanding of how natural comets operate, and now, an unprecedented international response that treats a harmless visitor like a potential threat. Let me be clear about what we're dealing with here. 3I/Atlas was discovered 4.5 months ago. Since then, multiple space agencies, dozens of observatories, and some of humanity's most advanced instruments have been trained on this object. The Hubble Space Telescope captured detailed images. The James Webb Space Telescope conducted infrared spectroscopy. The Very Large Telescope in Chile detected chemical emissions that have astronomers using words like puzzling and anomalous. Mars orbiters photographed it during close approach, and now, the International Asteroid Warning Network has done something it has never done in its 11 years of operation. Launched a formal observation campaign for an interstellar visitor. That campaign begins on November 27th, 2025, and runs through January 27th, 2026, exactly 2 months. And during that window, everything we're going to learn about 3I/Atlas will be learned. Everything we miss will be missed permanently. Because after late January, this object fades beyond detection threshold and disappears into the cosmic background forever. It came from another stellar system, billions of years old, carrying materials formed under conditions we can only infer, and we have one chance, one brief window, to understand what it is. July 1st, 2025. The Atlas Survey Telescope in Chile, part of a global network designed to detect near-Earth asteroids, captured images of an object moving through the inner solar system. At first glance, it seemed unremarkable, faint, distant, travelling on what appeared to be an unusual trajectory. But as follow-up observations came in from other telescopes around the world, something became clear. This object wasn't following the gravitational rules that govern objects born in our solar system. Within 24 hours, observations from the Zwicky Transient Facility in California confirmed what Atlas had found. This wasn't a periodic comet returning on a predictable orbit. This was something moving far too fast, on a path far too steep to be bound by the sun's gravity. Its trajectory was hyperbolic, a one-way trip through our cosmic neighborhood. And when astronomers traced that trajectory backward, projecting where it came from, the origin point lay somewhere beyond our solar system, somewhere in the direction of Sagittarius, near the galactic center. Pre-discovery images extended the observation record back to mid-June 2025. Amateur astronomer Sam Dean found Atlas observations from as early as June 5th. The object had been there, moving through dense star fields near the galactic center, difficult to discern against the background of countless stars. That's why it wasn't detected earlier. It was hiding in plain sight, camouflaged by the very brightness of our galaxy's core region. On July 2nd, multiple observatories confirmed what made this object special. It wasn't just an interstellar rock, it had a coma. A diffuse cloud of gas and dust surrounding a central nucleus. It was active, sublimating materials as solar radiation heated its surface. David Jewett and Jane Liu, using the Nordic Optical Telescope, reported that 3I Atlas was clearly active with cometary features. The 2-meter twin telescope at Teide Observatory in the Canary Islands confirmed the same thing. This was a comet, not an asteroid, an interstellar comet, only the second one ever confirmed, following 2I Borisov discovered in 2019. The designation 3I was official. The I stands for interstellar. The 3 inches marks it as the third confirmed interstellar object, after 1I Oumuamua in 2017 and 2I Borisov. The Atlas honours the survey that discovered it, and from that moment forward, 3I Atlas became the focus of intensive scientific scrutiny, unlike anything we'd seen for previous interstellar visitors. By the time the Minor Planet Center officially announced the discovery, they had collected 122 observations from 31 different observatories. Professional astronomers and citizen scientists alike were contributing data, building a picture of this visitor's characteristics, trajectory, and behavior. And what that picture revealed was deeply, profoundly strange. 3I Atlas is moving fast, really fast. When it entered the solar system, its velocity relative to the Sun was approximately 58 kilometers per second. That's 210,000 kilometers per hour. To put that in perspective, Earth orbits the Sun at about 30 kilometers per second. This interstellar visitor is travelling nearly twice as fast as our planet moves through space. It's moving faster than 1I Oumuamua, which had a velocity of 26 kilometers per second, faster than 2I Borisov at 32 kilometers per second. 3I Atlas holds the speed record for interstellar objects. That velocity tells us something crucial. This object has been travelling through interstellar space for an extraordinarily long time. Astronomers estimate at least 7 billion years, based on its trajectory and speed. 7 billion years. Our solar system is 4.6 billion years old. Earth is 4.5 billion years old. 3I Atlas is older than our planet. It formed around a star that might not even exist anymore, in a stellar environment billions of years removed from anything we can directly observe. We're looking at a time capsule from the ancient galaxy. The size estimates are less certain, but they're substantial. Based on observations through August 2025, the diameter of 3I Atlas's nucleus falls somewhere between 440 meters and 5.6 kilometers. That's an enormous range, reflecting the difficulty of separating the actual solid nucleus from the surrounding coma of gas and dust. At the small end, 440 meters, you're looking at an object roughly the size of a tall skyscraper. At the large end, 5.6 kilometers, you're looking at something the width of Manhattan Island. Either way, this isn't a small pebble. This is a substantial object with significant mass. If 3I Atlas were to impact Earth, which it absolutely will not, it would be catastrophic on a continental scale. Not a global extinction event, but civilization altering. Cities destroyed, climate disruption, millions of casualties. Fortunately, its trajectory keeps it far, far away from us. The closest approach to Earth occurs on December 19, 2025, at a distance of approximately 270 million kilometers. That's nearly twice the distance between Earth and the Sun. Mars, at its closest approach to Earth, comes within about 55 million kilometers. 3I Atlas never comes anywhere near that proximity. But here's what makes the trajectory genuinely remarkable. It's aligned. When you look at the path 3I Atlas is following through space, it aligns to within 5 degrees of the ecliptic plane. That's the flat disk that contains the orbits of all major planets in our solar system. Earth, Mars, Jupiter, Saturn, all of them orbit the Sun in roughly the same plane. And this interstellar visitor coming from outside our system, travelling through 3-dimensional space where any direction is equally probable, just happens to arrive on a trajectory that lines up with that plane. Astrophysicist Avi Loeb at Harvard calculated the probability of this alignment occurring by chance. It's about 0.2%, 1 in 500. Not impossible, but statistically unusual enough to warrant attention. If you're throwing darts at a 3-dimensional sphere from a random direction, hitting a target that's 5 degrees wide represents a very specific outcome. It suggests either remarkable coincidence or something else. Something we don't fully understand yet. The trajectory's shape is described by its orbital eccentricity. Elliptical orbits, like those of planets and most comets, have an eccentricity less than 1. Hyperbolic orbits, like 3I Atlas, have an eccentricity greater than 1. The eccentricity of 3I Atlas is approximately 6.1. That's extraordinarily high. It makes the trajectory appear almost straight rather than curved. This object is barely deflected by the Sun's gravity. It came in, swung around, and it's leaving, following a path that's more like a flyby than an orbit. In late July and throughout August 2025, something unexpected appeared in spectroscopic observations, atomic nickel vapor in the coma surrounding 3I Atlas, detected at wavelengths of 352 nanometers and 341 nanometers. Multiple observatories confirmed it independently. The Very Large Telescope in Chile, the Keck Observatory in Hawaii. The spectroscopic fingerprint was unmistakable. Nickel isn't unusual in cosmic objects. Most asteroids and comets contain metals formed in stellar cores and ejected during supernovae. Finding nickel in a comet's coma isn't shocking. What's shocking is the temperature at which this nickel was vaporizing. Nickel has a high sublimation temperature. You need sustained heat well over 1000 degrees Celsius to produce the kind of vapor emissions observed in the spectroscopic data. 3I Atlas, even at distances of 3 to 4 astronomical units from the Sun, is far too cold for that kind of natural vaporization. Solar radiation heats comet surfaces, yes, but we're talking about localized heating on the sunward side, not sustained high temperatures throughout the entire object. For nickel to appear in the coma at observed intensities, either there's a mechanism concentrating heat far beyond what solar radiation alone can produce, or the nickel is being released through some process other than simple thermal sublimation. Neither explanation fits standard comet behavior models. And then there's what's missing. Iron, nickel and iron are cosmic siblings. They form together in stellar nuclear synthesis. They're expelled together in supernovae. They bond together in asteroids and meteorites. The nickel-to-iron ratio in cosmic objects is remarkably consistent across our solar system. Finding nickel without corresponding iron is like finding smoke without a heat source. Technically possible, but it demands explanation. Dr. Avi Loeb, chair of Harvard's astronomy department, noted this discrepancy immediately. The nickel-to-iron ratio in 3I Atlas doesn't match any known natural comet or asteroid composition in our databases. It's not slightly off. It's dramatically inconsistent. Early observations showed strong nickel emissions, but no detectable iron at all. Later observations, as the comet approached perihelion and temperatures increased, finally detected iron, but the ratio remained abnormally skewed toward nickel. Loeb pointed out that certain nickel compounds, specifically nickel tetracarbonyl, exhibit characteristics similar to what's being observed. Those compounds are stable at much lower temperatures than pure nickel. They could explain the vapor emissions without requiring impossibly high heat. There's just one problem. Nickel tetracarbonyl is primarily known from industrial processes, from chemical manufacturing, from technology. On Earth, we produce it through the carbonyl process, which refines nickel by forming and then decomposing nickel tetracarbonyl. Now, before jumping to conclusions, let's be clear about what this means. Natural processes can produce nickel tetracarbonyl, in theory, under specific conditions involving carbon monoxide, nickel metal, and appropriate temperatures and pressures. The question is whether those conditions exist naturally in a comet nucleus, or whether we're seeing something that requires a different explanation. The composition of 3I Atlas makes this even more puzzling. Observations from the James Webb Space Telescope in August 2025 revealed that the comet's coma is dominated by carbon dioxide, approximately 87% carbon dioxide, 9% carbon monoxide, and only 4% water. That's essentially the opposite of what we see in standard solar system comets, which are typically water ice dominant. Dirty snowballs, that sublime water vapor as their primary volatile compound. 3I Atlas is a dirty dry ice ball, if anything. CO2-rich, water-poor, releasing nickel without iron, exhibiting chemical signatures that don't match the cometry models we've built from decades of observing comets in our own system. And the question that keeps coming up, the question that won't go away no matter how many natural explanations researchers propose, is this. Where did this object form that it acquired such an unusual composition? The hypothesis is that 3I Atlas formed in the outer regions of its home stellar system, far from its parent star, where temperatures were cold enough that carbon dioxide remained frozen while water vapor had already escaped or was never incorporated in significant quantities. That's plausible. Different stellar environments produce different chemical conditions. What forms around one star doesn't necessarily match what forms around another. But that hypothesis doesn't fully explain the nickel without iron anomaly. It doesn't explain why this specific combination of chemicals appears together in this specific object. It doesn't explain why the production rate of nickel relative to cyanide is higher than in 2I Borisov and orders of magnitude above the solar system comet median. These are documented facts from peer-reviewed observations, not speculation, and they resist easy incorporation into natural formation models. In September 2025, Hubble Space Telescope observations revealed another anomaly, a secondary feature pointing toward the Sun, an anti-tail. Comets develop tails as solar radiation and solar wind push gas and dust away from the nucleus. The tail always points away from the Sun. That's basic physics, radiation pressure, solar wind. The forces that shape comet tails are well understood and completely unidirectional. But Hubble images showed 3I Atlas with a feature pointing sunward, not exactly opposite the main tail, more like a forward-directed jet or stream. Avi Loeb and his colleagues offered a potential explanation. Ice fragments reflecting sunlight differently than dust could create an optical illusion of particles moving sunward when they're actually moving outward at different velocities. Larger particles travel slower, smaller particles travel faster, creating separation that looks like motion in the opposite direction when viewed from specific angles. It's a perspective effect, not actual reverse motion. That explanation fits physics. It's been proposed for similar features observed in solar system comets, though never confirmed with the clarity that Hubble images of 3Y Atlas provide. This would be the first clear case where we can study this phenomenon in detail. From a scientific perspective, that's valuable. It helps confirm theoretical models. But here's what makes this significant in context. This feature had never been documented with this degree of certainty in any solar system comet before. Proposed? Yes. Theorized? Yes. Observed with this specificity? No. 3I Atlas represents the first definitive observation. And when you add this to the unusual composition, the anomalous nickel emissions, the missing iron, the high velocity, the aligned trajectory, you're stacking anomalies. Each one individually has potential natural explanations. All of them together in the same object create a pattern that's harder to dismiss. The anti-tail observations got more interesting after perihelion. Images taken in November 2025 by amateur astronomers in Germany showed a network of jets around 3Y Atlas extending to distances larger than 1 million kilometers. Tightly collimated jets, not diffuse spreading. And here's the problem. 3I Atlas rotates with a period of approximately 16 hours. At the expected thermal speed of sublimated volatiles from a natural comet, about 400 meters per second, it takes about a month for material to traverse 1 million kilometers. How can these jets maintain their orientation if the nucleus is rotating every 16 hours? If gas is being ejected from specific regions on the surface, and the surface is rotating, those ejection points should sweep around like a lighthouse beam, creating a spiral pattern or diffuse fan, not tightly collimated straight jets. Unless the outgassing is somehow compensating for rotation, or unless the jets are being collimated by some mechanism we don't understand, or unless the rotation has slowed dramatically since the July observations, which seems physically unlikely. This is the 12th documented anomaly according to Loeb's running tally. Each one adds to the accumulating strangeness of this object. Each one resists simple incorporation into the normal comet category. And while none of them definitively prove anything extraordinary, taken together they create a profile that's unlike anything we've seen before. October 29th, 2025, at approximately 11:47 UTC, 3I Atlas reached perihelion, its closest approach to the Sun. The distance, 203 million kilometers, or 1.36 astronomical units, just inside the orbit of Mars. At that distance, solar irradiance reached roughly 770 watts per square meter, driving maximum thermal stress and activity on the comet's surface. This was the moment many astronomers had been waiting for. Perihelion is when comets typically display their most dramatic behavior. Increased heating causes increased sublimation, brighter comas, longer tails, sometimes fragmentation if the nucleus is weakly bound. It's the acid test, as Avi Loeb called it, for understanding what 3I Atlas truly is. If it's a natural comet held together by weak forces, perihelion heating might break it apart into fragments that evaporate more quickly, creating dramatic brightening and potentially revealing internal structure. If it's something else, perihelion might trigger different behavior. Maneuvering. Release of secondary objects, changes in trajectory beyond what gravity and outgassing can explain. This was the critical observational window, except there was one problem. Earth couldn't see it. 3I Atlas went into solar conjunction relative to Earth on October 21st, 8 days before perihelion. Solar conjunction is when an object lies directly behind the Sun as viewed from Earth. The Sun's glare drowns out everything in that region of sky. Ground-based telescopes can't observe anything within about 10 degrees of the Sun. Space-based coronagraphs can push that slightly, but even they have limits. 3I Atlas was effectively invisible from Earth during the most important phase of its passage. The timing is remarkable. Not suspicious necessarily, but remarkable. The object's trajectory brought it to closest solar approach at precisely the moment when the primary observing platform, Earth, was blind. Loeb has suggested this might be coincidence, or it might be design. If you were an extraterrestrial intelligence surveying the solar system, would you time your perihelion passage to occur when Earth-based observers couldn't see you? Would you use the Sun as a shield during your closest approach? That's speculation, but it's the kind of speculation that arises when you're faced with an object exhibiting multiple unexplained characteristics, following a trajectory that seems almost deliberately timed to avoid observation at critical moments. It's the kind of question that makes scientists uncomfortable because it ventures into territory where data is limited and imagination can run wild. But uncomfortable or not, it's a valid question to ask when the alternatives don't fully explain observations. Fortunately, Earth wasn't the only observation platform. Multiple spacecraft across the solar system had 3I Atlas in their sights during perihelion. The European Space Agency's Mars Express and Trace Gas Orbiter photographed the comet during its close approach to Mars on October 3rd, when the distance was only 29 million kilometers. NASA's Mars Reconnaissance Orbiter also captured observations, though data release was delayed due to the US. Government shutdown that affected NASA operations throughout October. The images from ExoMars Trace Gas Orbiter, taken with the Cassius camera, showed the comet's coma in detail from a vantage point much closer than any Earth-based telescope could achieve. Those observations helped refine 3I Atlas's trajectory by a factor of 10, reducing uncertainty about its position and future path. The triangulation of data from Mars orbit combined with Earth-based observations before and after conjunction created a much more precise picture of the object's motion through space. Space-based solar observatories also captured 3I Atlas during perihelion. The Stereo A spacecraft, which orbits the Sun ahead of Earth, observed the comet with its heliospheric images. The GOES weather satellites, which monitor Earth's environment but can also see objects near the Sun, detected 3I Atlas between October 18th and 24th. The SOHO Solar Observatory and the Punch satellite constellation tracked it as well, and the observations revealed something unexpected. 3I Atlas brightened dramatically near perihelion, not just the expected increase from enhanced solar heating, but a rapid brightening that exceeded predictions, and the colour changed. Observations showed the comet appearing bluer than the Sun, not redder, as you'd expect from dust scattering sunlight, and from a surface much colder than the Sun's photosphere, bluer, as if there were a heat source operating at temperatures higher than the surface should reach from solar heating alone. This is the 9th documented anomaly. A blue colour at perihelion that contradicts thermal models. Dust should redden scattered sunlight. A cold surface should emit in the infrared, not the blue, yet observations show blue. Loeb asks whether the object employs a power source hotter than the Sun. That's provocative language. It's also a fair question when observations don't match expectations and natural heating mechanisms don't explain the spectrum. Now, we come to the core question. Why did the International Asteroid Warning Network activate? The announcement came on October 21st, 2025, the same day as solar conjunction, the day 3I Atlas moved behind the Sun from Earth perspective. The Minor Planet Center published an editorial notice in its electronic circular MPEC 2025-U142. The text was precise and specific. Comets present unique challenges for accurate astrometric measurements and orbit predictions. Cometary bodies are extended with morphological features, comae and tails, that can systematically pull their centroid measurements off their central brightness peak. Presenting challenges to estimate comet trajectories, the International Asteroid Warning Network announces a comet campaign from November 27, 2025 through January 27, 2026 to introduce methods for improving astrometry from comet observations. The campaign will target Comet 3 for Atlas to exercise the capability of the observing community to extract accurate astrometry. On the surface, this makes complete sense. The International Asteroid Warning Network is a worldwide planetary defense collaboration of organizations and individual astronomers who work to detect, monitor, and characterize potentially hazardous asteroids and near-Earth objects. They conduct observing campaigns to test and refine the capabilities needed for tracking objects that might pose impact threats. They've done this roughly once a year since 2017. This is their 8th such campaign. Comets are indeed difficult astrometric targets. They're fuzzy. They have extended comas that obscure the central nucleus. Measuring the exact position of a diffuse glowing cloud is much harder than measuring a point-like asteroid. Small errors in centroid determination propagate into large trajectory uncertainties over time. For planetary defense, where you need to predict impact locations years in advance with kilometer-level precision, those errors are unacceptable. So using 3I Atlas as a training target makes strategic sense. It's a comet, presenting all the measurement challenges that planetary defenders need to master. It's observable from Earth during November and December, providing a sustained observation window. It's harmless, moving away from us, so mistakes cost nothing but learning opportunities, and it's generating high interest in the scientific community, which means participation will be strong. Perfect training scenario. But IOWN has never before launched a campaign for an interstellar object. Oumuamua received intensive study from individual observatories, yes, but no IAWN mobilization. 2I Borisov was observed extensively by professional astronomers worldwide, certainly, but no campaign structure, no registration requirements, no mandatory workshops. 3I Atlas is different. IAWN had been planning a comet astrometry campaign for fall 2025 since late 2024. That planning predates the discovery of 3 Atlas. So the framework was already in place, the infrastructure already designed. When 3I Atlas appeared, it became the logical target for that planned campaign. Convenient timing, a challenging comet appearing right when IAWN wanted to practice comet observations. But the specifics of the campaign suggest something beyond routine practice. Registration is required by November 7, 2025. That's 17 days from the announcement. For astronomical campaigns, that's an extremely tight deadline. Professional observatories schedule telescope time 6 to 12 months in advance. Research grants require planning. International coordination demands logistics. Yet IAWN is demanding commitment within 2.5 weeks. There's a mandatory workshop on November 10, 2025. Attendance is required for campaign eligibility. If you don't register by November 7th and attend the workshop on November 10th, you're excluded from official participation. That's unusual. Astronomy is traditionally collaborative and open. Observations are published, methodologies are shared, data is made available. But this campaign creates barriers, prerequisites, controlled access. What are they teaching in that workshop that requires restricted access? The stated purpose is standardization. Teaching participants how to measure comet positions consistently so data from different observatories can be combined reliably. That's entirely reasonable. When you're aggregating measurements from dozens of sources worldwide, you need everyone using compatible methodologies. Position measurements must reference the same coordinate systems. Brightness measurements must account for instrumental differences. Timestamps must synchronize precisely, but it also means knowledge stratification. After November 10th, there are 2 groups: those who attended the workshop and know what they're looking for, and those who didn't and are observing blind. The workshop content hasn't been published. We don't know what specific techniques are being emphasized, what particular features observers are being told to prioritize. That information remains internal to campaign participants, creating information asymmetry between insiders who see the full picture and outsiders who see fragments. The campaign also opens participation to citizen scientists. Amateur astronomers with backyard telescopes are invited to contribute observations. That's unprecedented for an IAWN operation. Professional coordination is standard. Citizen inclusion is not. It suggests they need volume, maximum coverage, as many observation points as possible distributed globally, capturing data from diverse locations and atmospheric conditions. Volume matters more than individual instrument quality. Why would volume matter for training? Because you're testing coordination at scale, ensuring data aggregation systems can handle inputs from hundreds of sources, validating that international communication channels work efficiently under load. That fits the training narrative. But volume also matters for verification. If you need consensus, if you need to confirm observations independently across multiple platforms, so no single source can be dismissed as instrumental error or measurement artifact. If you need to build a dataset robust enough that findings become undeniable regardless of how unusual they might be, you need volume. You need hundreds of observers all seeing the same thing. Let's step back and think about what planetary defense actually demands. It's not just about moving asteroids, that's the final step. Before you can deflect an object, you need to detect it, track it, characterize it, assess whether it poses a threat, decide whether intervention is warranted, plan a deflection mission, build and launch the spacecraft, execute the intercept, confirm success. Each step is complex. Each step has failure modes, and the entire chain depends on accurate astrometry. In September 2022, NASA's DART mission successfully demonstrated kinetic deflection. The double asteroid redirection test deliberately crashed a spacecraft into Dimorphos, a small asteroid moon orbiting the larger asteroid Didymos. The impact changed Dimorphos's orbital period by 33 minutes, proving that we can alter an asteroid's trajectory. The physics works. The technology is operational. But DART had advantages that real-world scenarios might not provide. Dimorphos was a known quantity. Astronomers had tracked it for years. They knew its orbit precisely, its size, its rotation, its relationship to Didymos. DART launched 10 months before impact, giving engineers time to refine trajectory, make course corrections, validate systems. The impact point was calculated with extreme precision. When DART hit, it hit exactly where planned. What DART didn't test was finding an unknown object with minimal warning and tracking it accurately enough to plan an interception mission under time pressure. That's where astrometry becomes critical. If you can't predict where the asteroid will be, you can't plan an intercept. If your position measurements have systematic errors you don't understand, your trajectory calculations become increasingly wrong over time. If the object is a comet with unpredictable outgassing affecting its motion, the difficulty multiplies. From this perspective, 3I Atlas genuinely is an ideal training target. It's a comet, so observers must deal with all the astrometry challenges. It's moving fast, creating compressed observation windows similar to what responders would face with minimal warning. It's compositionally unknown, forcing characterization without prior knowledge. It appeared from interstellar space simulating unexpected arrival, and critically it's harmless so mistakes cost nothing. The campaign structure mirrors full planetary defense response. Registration establishes participants. The workshop trains on standardized methodologies. The observation window creates sustained coordinated effort. Data aggregation tests real-time information sharing across international borders. This isn't abstract planning, this is operational validation, testing whether infrastructure works when activated under realistic conditions. But here's the deeper question. If this is training, what scenario are they training for? The stated purpose is improving astrometry techniques, fair enough. But the scope of mobilization exceeds what astrometry practice alone requires. The involvement of multiple space agencies, the real-time data aggregation, the international coordination protocols, that's full-spectrum planetary defense activation. They're not just practicing measurements, they're practicing the entire response framework. Maybe the scenario they're training for isn't can we measure comets accurately? Maybe it's can we coordinate globally on a compressed timeline when facing an object we don't fully understand? That's a different question with different implications. It means the training value isn't technical, it's organizational. Testing whether international cooperation works under pressure, whether data sharing happens quickly enough, whether consensus can be reached when uncertainty is high and time is limited. And if that's the real test, then the anomalous characteristics of 3I Atlas aren't incidental. They're central, because uncertainty is what makes coordination difficult. If everyone agrees the object is a normal comet, coordination is easy. If the object exhibits characteristics no one can explain, if researchers disagree on interpretation, if data suggests multiple incompatible scenarios, coordination becomes challenging. Trust breaks down. Nations hesitate to commit resources based on uncertain threat assessments. That would explain why they chose 3 Atlas specifically. Not because it's a typical comet, but because it's an atypical one. One that forces participants to coordinate despite uncertainty, to reach consensus despite ambiguity, to function effectively even when they don't fully understand what they're observing. That's the real test of planetary defense readiness. Not technical capability, but institutional resilience under conditions that resist easy answers. No discussion of 3I Atlas would be complete without addressing Dr. Abraham Avi Loeb, the Frank Baird Jr. Professor of Science at Harvard University, former chair of Harvard's Astronomy Department, founding director of the Black Hole Initiative, over 1,000 peer-reviewed papers published, advisor to numerous PhD students, member of the President's Council of Advisors on Science and Technology. By conventional academic metrics, he's one of the most accomplished astrophysicists alive. He's also, depending on perspective, either a visionary willing to ask uncomfortable questions or a scientist who sacrificed rigorous skepticism for public attention. Both assessments contain truth, and the tension between them defines why his voice matters in the 3I Atlas conversation. Loeb first became widely known with Oumuamua, the first confirmed interstellar object detected in October 2017. Oumuamua exhibited strange acceleration, deviations from what gravity alone would predict. For typical comets, that's explained by outgassing, jets of vapor acting like tiny rocket thrusters. But Oumuamua showed no visible coma, no gas emissions, no dust tail, nothing that would explain observed acceleration through standard mechanisms. Loeb, along with his postdoc Shmuel Bialy, published a paper in Astrophysical Journal Letters proposing that one possible explanation was a light sail, a thin reflective surface pushed by solar radiation pressure, artificially constructed, potentially of technological origin. They didn't claim this was definitely true. They argued it was a hypothesis worth considering alongside natural explanations. The scientific community largely rejected this interpretation, favouring explanations like hydrogen iceberg outgassing or non-standard comet behaviour. But Loeb's willingness to seriously propose artificial origin made him instantly controversial. To some, he became a hero, a scientist brave enough to consider possibilities others dismissed out of fear of ridicule. To others, he became a cautionary tale, proposing speculative ideas without sufficient evidence. Both reactions missed the nuance. Loeb isn't claiming Oumuamua was definitely artificial. He's arguing we can't definitively rule it out based on available data, and that dismissing the possibility without investigation is itself unscientific. His position is that when you observe something genuinely anomalous, you should consider all explanations that fit the data, including unconventional ones, rather than forcing observations into existing frameworks. Now he's turned attention to 3I Atlas. His analysis focuses on specific technical anomalies: the nickel emission without iron, the CO2-dominated composition, the anti-tail phenomenon, the aligned trajectory, the size and velocity combination, each one documented, each one published in peer-reviewed observations, each one representing something we haven't seen before or haven't seen in this combination. Loeb uses the term black swan event to describe what 3I Atlas might represent. The phrase comes from risk analysis. A black swan is an unpredictable event with massive consequences that seems obvious only in hindsight. The 2008 financial crisis, the 9/11 attacks, the COVID-19 pandemic, events that were theoretically possible but not anticipated, whose occurrence fundamentally changed perspectives. He's suggesting 3I Atlas might be that kind of event. Not in terms of physical danger, there's no collision risk, but in terms of what its true nature might reveal about the universe we inhabit. If it's a natural comet formed through processes we don't understand, that expands our knowledge of stellar chemistry and planetary system formation. If it's something else, that changes everything about our place in the cosmos. His Trojan horse analogy is deliberately provocative. In the original Greek myth, the Trojans saw a wooden horse and interpreted it as a gift based on their cultural context. It wasn't. Loeb asks, if an advanced civilization wanted to study our solar system, Would we recognize their probe, or would we categorize it as a comet because that fits our existing frameworks? Are our classification systems sophisticated enough to distinguish between natural and artificial objects if the artificial ones are designed to look natural? He's developed what he calls the Loeb scale, a ranking system for objects based on their anomalous characteristics. It ranges from 1 to 10, with 1 being clearly natural and 10 being clearly artificial. He ranks 3I Atlas as a 4, not definitely artificial, but anomalous enough to warrant serious investigation. The ranking is based on cumulative probability. Each individual anomaly has a certain likelihood of occurring naturally. Multiply those probabilities together, accounting for the fact that all these anomalies appear in the same object, and you get vanishingly small overall probability. The scientific community's response has been measured. Most astronomers studying 3Y Atlas haven't publicly endorsed the artificial hypothesis. Many acknowledge the chemical anomalies warrant further study, but argue that jumping to artificial explanations is premature when natural processes we don't fully understand remain unexplored. That's appropriate scientific conservatism. But Loeb's voice matters regardless of whether his most provocative suggestions are correct. He's reframing the question. Instead of asking why use 3 Atlas for training, he's asking why use an object with these specific anomalies, because planetary defense training works best with representative scenarios, not edge cases. The fact IA-11 chose 3 Phi Atlas specifically, with its nickel emissions, unusual composition, and anomalous features, suggests those characteristics are part of why the campaign exists, not incidental details. November 7th, 2025. Registration deadline. Astronomers worldwide who want to participate in the IAWN campaign must commit by this date. Professional observatories, university research groups, amateur astronomers with suitable equipment, all submitting their information, confirming their participation, agreeing to the observation protocols. November 10th, 2025, the mandatory workshop. 1500 UTC. Campaign participants gather virtually for training on astrometry methodologies specific to 3Y Atlas observations. The content isn't public. We don't know exactly what's taught, what specific techniques are emphasized, what features observers are told to prioritize. That information circulates only within the participant community. November 27th, 2025. Campaign begins officially. Coordinated observations start. Telescopes across 6 continents from professionals to citizen scientists, all turning their attention to the same target, all following standardized protocols learned in the workshop, all submitting data to the Minor Planet Center for real-time aggregation and analysis. The observation window runs through January 27th, 2026, 2 months. During that time, 3I Atlas will be visible in the pre-dawn sky, moving through the constellations Virgo and Leo, gradually dimming as it increases distance from the Sun. By late November, it's bright enough for detailed study with moderate-sized telescopes. By late January, it approaches the threshold of detectability even for large professional instruments. The campaign window captures the optimal observation phase. After January, the object fades beyond reach. What are observers looking for? Position measurements primarily, astrometry, tracking the comet's motion against background stars with extreme precision, but also photometry, monitoring brightness changes that might indicate outbursts or surface activity, spectroscopy where possible, analyzing light to determine composition and search for unexpected emission lines, and imaging, documenting structure, coma morphology, any changes in appearance. The data flows to the Minor Planet Center at Harvard University, the global clearinghouse for small body observations. There, specialists process submissions as they arrive, updating 3 Atlas's orbital parameters continuously, refining trajectory calculations, integrating measurements from diverse sources into a coherent picture. This is operational tempo, real-time data handling, the same workflow that would activate during an actual planetary defense scenario. And the participants don't see the complete picture. Individual observers contribute measurements without knowing what the aggregated dataset reveals, without seeing how their observations combine with everyone else's to show patterns or changes invisible in isolated data points. Only campaign coordinators at the Minor Planet Center and IAWN see the full synthesis. That information asymmetry is by design. You can't have hundreds of researchers independently interpreting incomplete datasets and reaching conflicting conclusions. Centralized analysis ensures consistency, but it also means transparency depends on what coordinators choose to release and when they choose to release it. During the campaign, the public sees individual observations published in astronomical telegrams and circulars. After the campaign, presumably, comprehensive analysis appears in peer-reviewed papers. But during those critical 2 months when 3I Atlas is observable and data is accumulating, only the inner circle knows what the full picture shows. The European Space Agency's Jupiter Icy Moons Explorer JUICE passed within 64 million kilometers of 3I Atlas on November 4, 2025. Multiple instruments observed the comet: the Janus Visible Imager, the Magis Infrared Spectrometer, the SVI Submillimeter Wave Instrument. Unfortunately, JUICE is currently using its main high-gain antenna as a heat shield because it's relatively close to the Sun in its orbit. It's transmitting data back to Earth at much slower rates through its medium-gain antenna. We won't receive JUICE's observations of 3I Atlas until February 2026. That data could be significant. JUICE had one of the best vantage points for observing 3I Atlas in a highly active state. Its instruments can analyze composition in detail, measure temperature distributions, detect subtle features invisible from Earth. When that data arrives and gets processed, it will add substantially to our understanding of what this object is. In March 2026, 3I Atlas will pass within 54 million kilometers of Jupiter. NASA's Juno spacecraft, orbiting Jupiter since 2016, might be able to observe the comet during that encounter. There's been discussion about whether Juno could be redirected to perform a close flyby of 3I Atlas, potentially becoming the first spacecraft to intercept an interstellar object. That would be historic. Direct, high-resolution imaging of the nucleus, detailed spectroscopy, particle analysis if Juno passed through the coma, data quality far exceeding anything telescopes can provide. But Juno is low on fuel. Its main engine has issues. Redirecting it would require propellant that might be needed for the spacecraft's primary mission, and the maneuver would have to be executed soon, in late 2025 or early 2026, to position Juno for intercept in March. As of now, NASA hasn't announced plans to redirect Juno. The decision depends on mission priorities, available resources, and technical feasibility, but the possibility remains on the table. The Mars Reconnaissance Orbiter captured observations of 3I Atlas on October 2, 2025, when the comet passed within about 30 million kilometers of Mars. The HiRISI camera, the highest resolution imaging system currently operating beyond Earth, photographed the comet. Those images should have resolution approximately 3 times better than the best Hubble observations. They could reveal surface features, measure the nucleus size more precisely, separate the solid body from the surrounding coma more clearly. But those images haven't been released yet. Delayed by the NASA government shutdown that affected operations throughout October, Congresswoman Anna Paulina Luna has been working to get those high-res images released to the scientific community. They represent some of the most detailed observations of 3I Atlas available, captured at close range from an optimal viewing angle. When they become public, they'll contribute significantly to understanding the object's physical structure. Ground-based observations continue. Amateur astronomers have captured images showing evolving coma structure and jet features. Professional observatories conduct follow-up spectroscopy searching for additional emission lines or changes in composition as the comet moves farther from the Sun. The Virtual Telescope Project hosted a public livestream in mid-November, providing real-time views of 3I Atlas, for anyone interested in seeing this interstellar visitor with their own eyes, remotely at least, through robotic telescopes in Italy. The observations will continue through late January. Then 3I Atlas fades. It doesn't disappear instantly. It gradually dims as distance increases, dropping below detection thresholds for progressively larger telescopes. By spring 2026, only the absolute largest instruments might still detect it, and barely. By summer, it's gone. Back into the interstellar medium from which it came, carrying its mysteries with it, leaving behind data sets and questions and debates that will continue long after the object itself has vanished from our view. 3I Atlas is the third confirmed interstellar object. We know of 3. How many have passed through undetected? How many pass through every year that we simply don't see because our telescopes aren't sensitive enough or aren't pointing in the right direction at the right time. Statistical models suggest interstellar objects are common. Not rare anomalies, but constant background traffic flowing through the galaxy. Every stellar system occasionally ejects material. Comets scattered by gravitational interactions with planets. Asteroids perturbed by close stellar encounters. Planet fragments from catastrophic collisions. All of that debris drifts through interstellar space, travelling for millions or billions of years until crossing another stellar system's path. Our galaxy contains approximately 300 billion stars. Even if only a tiny fraction eject material into interstellar space, that's billions of objects adrift. Not all large enough to detect from Earth. Not all on trajectories that bring them through the inner solar system where we have telescopes watching, but present nonetheless, a constant rain of matter from elsewhere, mixing compositions from different stellar environments, creating chemical diversity we're only beginning to appreciate. The Vera Rubin Observatory, beginning operations now in late 2025, will revolutionize detection. It's designed to photograph the entire visible sky every few nights with sensitivity far exceeding previous surveys. Rubin will detect faint objects, fast-moving objects, objects that previous instruments would miss. Astronomers estimate it will find dozens, possibly hundreds of interstellar objects over the next decade. We're about to go from interstellar visitors being rare curiosities to routine occurrences we catalogue regularly. That changes everything. Currently, each detection is major news, international coordination, intensive observation, maximum scientific effort. But when we're detecting multiple interstellar objects yearly, that response becomes unsustainable. We'll need triage systems, criteria for determining which visitors warrant intensive study, and which get catalogued with basic observations. We'll need frameworks for rapid characterization, for deciding quickly whether an object is interesting enough to mobilize resources. The 3I Atalas campaign might be teaching us those frameworks, how to coordinate efficiently without mobilizing every available asset for every detection, how to assess quickly whether something merits deeper investigation or can be filed as normal interstellar rock, nothing unusual, catalogue, and move on. How to function in a future where the exotic becomes routine and the truly anomalous needs to stand out against a background of merely interesting. But it also raises a question that makes some scientists uncomfortable and others fascinated. If interstellar objects are common, if hundreds pass through the solar system regularly, what's the probability that at least one of them is artificial? Not naturally formed comet or asteroid, but technological artifact, probe, spacecraft. Whatever form advanced civilizations might use for exploration. The math isn't crazy. Our galaxy has existed for over 13 billion years. 300 billion stars. If even a tiny fraction produced technological civilizations at some point in their existence, that's millions of civilizations, not all existing simultaneously, but cumulatively over galactic history. If even a tiny fraction of those civilizations send probes into interstellar space for exploration or research, that's thousands of artificial objects potentially drifting through the galaxy alongside billions of natural ones. Natural objects vastly outnumber artificial ones. The probability of any single detection being artificial is low, but the probability that we've never encountered an artificial object, given the numbers involved, might be lower than we think. Small but non-zero, and small but non-zero is exactly the probability space we should be prepared to recognize when we see it. This is where planetary defense and the search for extraterrestrial intelligence converge. SETI traditionally focused on radio signals, intentional communications broadcast from civilizations trying to make contact. But if technological species send probes rather than broadcasts, if exploration is physical rather than electromagnetic, then detection becomes the same challenge as planetary defense. Finding and tracking objects moving through space. The telescopes are identical. The techniques are identical. The difference is interpretation. Is this rock or artifact, natural or artificial? And increasingly researchers recognize that distinction might not be obvious. If a civilization wanted to explore stellar systems, would they send obviously artificial spacecraft? Or would they design probes to mimic natural objects, allowing undetected observation without triggering response from inhabitants? Stealth isn't about malevolence, it's about not contaminating observations. If you're studying something, you don't want your presence to alter its behavior. You observe without interfering, which means artificial objects, if they exist, might be specifically designed to look natural, We'd categorize them as comets or asteroids because that's what our classification systems expect. And we'd never know the difference unless we looked for technological signatures specifically, emission patterns inconsistent with thermal processes, structural features suggesting construction rather than accretion, trajectory changes indicating propulsion beyond gravity and outgassing, electromagnetic signals, anything requiring technology to explain. The only way to rule out artificial origin definitively is to look for it systematically and not find it. Dismissing the possibility without investigation doesn't prove natural origin, it just proves you didn't look. That doesn't mean assuming everything is artificial, that's equally unscientific. The correct approach is agnostic investigation. Observe thoroughly, analyze carefully, look for characteristics that would distinguish artificial from natural. If you find nothing, tentatively classify as natural while acknowledging limitations. If you find anomalies, investigate further until natural or artificial explanation clearly fits. That's what makes the 3I Atlas campaign significant regardless of outcome. The observation intensity, the data quality, the international coordination, this represents our best attempt yet to thoroughly characterize an interstellar visitor. Whether it's natural or artificial, we'll learn more about it than we learned about Oumuamua or Borisov. We'll expand our database of interstellar object characteristics, and if it's natural, that database helps us understand what natural looks like, making future artificial detection easier by establishing baseline. If it's artificial, that's obviously paradigm shifting. Either outcome advances understanding. Mark your calendars. December 19th, 2025, 6 days before Christmas, 3I Atlas reaches its closest point to Earth. The distance, approximately 269 million kilometers, or 1.8 astronomical units, nearly twice the distance between Earth and the Sun, completely safe, no collision risk whatsoever, but significant nonetheless, because this represents our last optimal viewing opportunity before the object dims beyond practical observation. Avi Loeb, with his characteristic blend of scientific precision and provocative framing, told Newsweek, on December 19th, 2025, 3I Atlas will be closest to Earth. My hope is that it will not deliver to Earth any unwanted gifts for the holidays. He added that the comet can be observed with any telescope having an aperture larger than 30 centimeters, roughly 12 inches. That puts it within reach of serious amateur astronomers with moderate equipment and dark skies. The timing is almost poetic in its symbolism. An ancient visitor from another stellar system, billions of years old, making its closest approach to Earth during the holiday season. A cosmic gift, in a sense, whether it turns out to be a remarkable natural comet teaching us about stellar chemistry elsewhere in the galaxy, or something that challenges our assumptions about what travels through interstellar space. By mid-December, 3I Atlas will be moving through the constellation Leo, the Lion, gradually dimming as it increases distance from both the Sun and Earth. Its apparent magnitude will be hovering around 12 or 13, requiring telescopes to see it all, appearing as a faint fuzzy patch against the background stars. Not spectacular to the naked eye, not a dramatic sight like Comet Hale-Bopp or Comet Neowise, but scientifically invaluable, carrying information encoded in its light, its spectrum, its motion. Ground-based observatories will be conducting intensive observations around this time. The IAWN campaign will be in full swing, with coordinated measurements being submitted to the Minor Planet Center daily. Professional astronomers will be using large telescopes to conduct spectroscopy, searching for changes in composition as the comet cools while moving away from perihelion. Are the nickel emissions continuing? Has iron become more prominent in the spectrum? Are there other emission lines appearing that weren't visible during the hotter, more active phase near the Sun? Amateur astronomers will be contributing as well. Those who registered for the IAWN campaign and attended the November 10th workshop will know exactly what measurements to prioritize, what standards to follow, how to calibrate their observations for consistency with professional data. But even observers outside the official campaign can contribute, photographing the comet, documenting its position against background stars, measuring its brightness. Every observation adds to the data set. Every measurement helps refine our understanding. The December approach is also when the James Webb Space Telescope and Hubble Space Telescope might conduct additional observations. Webb's infrared sensitivity can detect subtle temperature variations across the coma, map the distribution of carbon dioxide and other volatiles, search for organic molecules that might be present in the gas emissions. Hubble's ultraviolet and visible light capabilities can track the dust distribution, measure the coma's expansion rate, look for structural changes in the nucleus if the perihelion heating caused any fragmentation. Loeb's comment about unwanted gifts is tongue-in-cheek but reflects genuine curiosity about whether 3 Atlas might exhibit any behavior during Earth's closest approach that would be difficult to explain through natural mechanisms. If it's a natural comet, we expect predictable behavior. Gradual dimming as distance increases, decreasing gas emissions as solar heating diminishes, continued motion along a purely gravitational trajectory, modified only slightly by outgassing momentum. Standard comet physics. If it's something else, December 19th represents a moment when any deviation from expected behavior would become apparent. Course corrections, release of secondary objects, sudden brightening without corresponding increase in solar heating, electromagnetic emissions beyond what thermal processes produce, radio signals. Anything anomalous would stand out starkly against the baseline of normal cometary activity, established through months of observations. This is what makes the IAWN campaign timing so strategic. The observation window extends from late November through late January, bracketing the December 19th closest approach. Maximum observational resources concentrated during the period when 3I Atlas is most accessible from Earth, when any unusual behavior is most likely to be detected, when the data quality will be highest. After December 19th, the comet continues moving away. Earth and 3Y Atlas are both orbiting the Sun, but on diverging paths. The distance increases steadily. By early January, it's noticeably dimmer. By late January, when the IAWN campaign officially ends, it's approaching the limit of what moderate-sized telescopes can detect. By February, only the largest professional instruments can track it. By spring, it's effectively invisible, lost in the cosmic background. The December approach is a milestone, a peak in the story of humanity's encounter with this interstellar visitor. The moment when our planet and this ancient traveller from elsewhere in the galaxy pass closest to each other in their respective journeys through space, ships passing in the cosmic night, briefly close enough for detailed study before diverging forever. Understanding what makes observing 3 Atlas challenging helps appreciate why the IAWN campaign structure makes sense. This isn't like photographing the Moon or Jupiter. This is detecting a faint, fuzzy object moving rapidly against background stars, extracting precise position measurements from that fuzzy glow, and doing so repeatedly over weeks and months to track its motion with extreme accuracy. The first challenge is simply finding it. At magnitude 12 or 13, 3I Atlas is invisible to the naked eye. You need a telescope. But pointing a telescope at the right spot in the sky requires knowing where the object is supposed to be at any given moment. That requires ephemerides, predicted positions calculated from the object's orbit. The Minor Planet Center publishes updated ephemerides regularly as new observations refine the orbital parameters. Observers download those predictions, input them into their telescope control systems, and slew to the predicted coordinates. But predictions have uncertainty. Even with excellent orbital calculations, there's a search area, maybe a few arc-minutes across. That's not large on cosmic scales. But in a telescope's narrow field of view, it means carefully searching, comparing what you see against star charts, looking for the one fuzzy spot that wasn't there in reference images taken months or years earlier. Finding the comet requires patience and attention to detail. Once located, the next challenge is measurement. Position astrometry requires determining the comet's coordinates relative to background stars, whose positions are known with extreme precision. You photograph the field. Software identifies stars in the image. Those stars are matched against catalogues, massive databases containing positions of billions of stars measured by satellites like Gaia, with micro-arc-second accuracy. The software calculates exactly where your telescope was pointing, based on which stars appear in the frame and where they appear. Then comes the hard part. Where exactly is the comet in that image? It's not a point source like a star. It's an extended, fuzzy blob. The coma of 3Y Atlas, based on observations from July, had an angular diameter of about 2 arcseconds for the brightest central region and up to 10 arcseconds for the full extent. That's tiny. At arm's length, 10 arcseconds is roughly the angular size of a human hair seen from across a room. But in astronomical measurements, where you're trying to determine positions to within fractions of an arcsecond, that fuzziness creates uncertainty. The standard technique is centroid measurement. Software analyzes the brightness distribution across the fuzzy blob, calculates the geometric center of that distribution, and reports that center as the comet's position. But here's the problem. The brightest part of the coma doesn't necessarily coincide with the nucleus location. Gas jets, preferential emission from the sunward side, asymmetric dust distribution, all of these create brightness patterns that shift the centroid away from where the actual solid nucleus sits. That's what the IAWN campaign is designed to address. Training observers to recognize these systematic offsets, to account for them in their measurements, to use techniques that minimize the error. Different software algorithms produce different centroids from the same image. Different observers using different equipment introduce different instrumental biases. The workshop teaches standardization. Use this software, use these settings, process the data this way, report measurements in this format. Standardization isn't about stifling creativity. It's about making measurements comparable and combinable. Then there's timing. Precise astrometry requires knowing exactly when the observation was made. Timing errors translate directly into position errors because the comet is moving. At 58 kilometers per second, 3 fuzzy atlas travels its own diameter, assuming 5 kilometers, in less than 2 minutes. If your observation timestamp is off by even 30 seconds, your reported position might be off by nearly 30 kilometers. For an object hundreds of millions of kilometers away, that 30-kilometer error seems negligible. But when you're trying to predict trajectories months or years into the future, those small errors compound. Modern telescopes use GPS time synchronization, ensuring their clocks are accurate to within milliseconds. Observers must verify their timing systems are functioning correctly, that exposures are time-stamped properly, that data headers contain accurate observation times. Small details that seem trivial but matter enormously when data from hundreds of observers is being aggregated. Photometry, measuring brightness, faces similar challenges. How bright is 3D Atlas? Sounds like a simple question. It's not. Brightness varies with distance from both the Sun and Earth, following predictable patterns based on geometry and solar heating. But it also varies unpredictably with outbursts, when sudden releases of gas brighten the coma temporarily. It varies with viewing angle, as different regions of the nucleus rotate into view. It varies with aperture size, the diameter of the measuring area, because larger apertures capture more of the extended coma. Standardizing photometry requires defining measurement protocols. Use a specific aperture size, say 10 arcseconds diameter. Measure the total light within that aperture. Compare against reference stars in the same image whose brightnesses are known. Report the magnitude using standard filter systems, like the Johnson-Cousins system that astronomers have used for decades. Consistency allows comparison. Without consistency, brightness measurements from different observers can't be reliably combined. Spectroscopy, analyzing light to determine composition, presents the highest technical difficulty. You need large telescopes, sophisticated instruments, careful calibration. The light from 3Y Atlas is faint. Spreading that light into a spectrum, separating it into component wavelengths, makes it even fainter. You need long exposures, sometimes hours, to collect enough photons for analysis. And you need to account for Earth's atmosphere, which absorbs certain wavelengths, distorts others, adds its own emission lines that contaminate the spectrum. Professional observatories have the equipment and expertise for high-quality spectroscopy. But even professionals face challenges. The very large telescope observations that detected nickel required carefully designed observation strategies, optimal sky conditions, extensive data processing to extract clean spectra from the raw data. Every emission line must be identified, its wavelength measured precisely, its intensity calibrated against known standards. That's why the nickel detection was significant. It required real effort, real skill, real attention to detail. The IAWN campaign coordinates all of this. Position measurements from amateurs and professionals alike combined into a coherent trajectory. Brightness measurements standardized across observers, revealing the comet's light curve, its evolution over time, spectroscopic observations from major facilities, providing compositional data that ground-based photometry can't reveal. All flowing into the Minor Planet Center, where specialists integrate everything into a comprehensive picture of what 3I Atlas is and how it's behaving. This is modern observational astronomy. Not one heroic observer making a solitary discovery, but networks of people contributing pieces of a puzzle, using standardized methods to ensure compatibility, trusting central coordination to synthesize individual observations into collective understanding. It's complex, it's bureaucratic in some ways, but it works. It's how we've built our knowledge of the solar system and beyond. To fully appreciate 3I Atlas, we need context. What came before? How does this visitor compare to the previous interstellar objects humanity has detected? Because each one has taught us something different, each has raised new questions, each has shaped our expectations for what interstellar travelers might be like. Oumuamua, the name is Hawaiian, meaning scout or messenger from afar arriving first. Discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii. The first confirmed interstellar object ever detected. And it was bizarre from the start. Oumuamua was small, maybe 100 meters long, pancake-shaped or cigar-shaped depending on interpretation. It tumbled as it traveled, causing brightness variations as different faces caught sunlight. It exhibited anomalous acceleration, speeding up slightly beyond what gravity alone predicted. For comets, such acceleration is expected from outgassing, but Oumuamua showed no visible coma, no gas emissions, no dust tail, nothing that would explain the acceleration through standard mechanisms. Avi Loeb proposed that a light sail, a thin reflective surface pushed by solar radiation pressure, could explain both the shape and the acceleration. Natural formation? Perhaps an interstellar iceberg of hydrogen ice, which wouldn't produce visible gas emissions. Or perhaps something artificial. The debate continues. We'll never know for certain because Oumuamua left the solar system before we could study it adequately. It was already outbound when discovered, visible for only a few weeks before dimming beyond detection. The lesson from Oumuamua: interstellar objects can behave in ways we don't immediately understand. Our comet models are built from studying objects in our solar system. When something from elsewhere exhibits different characteristics, those models might not apply. We need flexibility in interpretation, willingness to consider multiple hypotheses, and most importantly, we need to observe thoroughly while we have the chance. 2I Borisov, discovered on August 30, 2019 by amateur astronomer Gennady Borisov using a homemade 65cm telescope. The second confirmed interstellar object, and this one was clearly a comet from the start. It had a visible coma, it had a dust tail. It brightened as it approached the sun and dimmed as it receded. Spectroscopic observations showed carbon monoxide and water, typical cometary volatiles. It behaved like comets in our solar system behave. But it wasn't identical. Its composition showed some differences. The dust was redder than typical solar system comet dust. The carbon monoxide to water ratio was higher than most solar system comets exhibit. Not wildly different, but measurably distinct. Enough to suggest that comets from other stellar systems might have subtle compositional variations reflecting different formation environments. 2I Borisov taught us that, while interstellar comets can be broadly similar to solar system comets, confirming that basic comet physics is universal, the details matter. The specific chemistry, the dust properties, the volatile ratios, these encode information about where the comet formed, what conditions prevailed in its birth environment, what processes shaped it over billions of years. Now 3I Atlas, the third confirmed interstellar visitor, and it's different again. Not like Oumuamua's inexplicable behaviour, not like Borisov's comfortable familiarity, something in between, clearly a comet with coma and activity, but with chemical signatures that don't quite match. Nickel without iron, CO2 without much water, anti-tail features that theory predicts but observations rarely confirm. A line trajectory that's statistically improbable but not impossible. Each interstellar object expands our understanding. Each one shows us that the category interstellar visitor encompasses diversity. They're not all the same. Different origins, different compositions, different behaviours. That's actually reassuring in a way. It means the universe is complex and interesting. It means there's genuine variety out there. Not just monotonous repetition of the same types of objects, but it also means we can't assume. We can't take one or two examples and extrapolate confidently about what all interstellar objects should be like. We need more data, more detections, more opportunities to study these visitors in detail before they leave. That's what makes Vera Rubin Observatory so important. It will find more, many more, and with each new detection, we refine our understanding, expand our categories, sharpen our ability to recognize what's normal variation versus what's genuinely anomalous. The historical progression from Oumuamua through Borisov to 3-Sun Atlas shows us learning in real time. First object, confusing insufficient data, left us with more questions than answers. Second object, clearer, more observation time, confirmed that interstellar comets exist and mostly behave as expected. Third object, even better observation, unprecedented coordination, revealing that even comets that mostly behave as expected can have surprising characteristics that warrant deep investigation. This is how science progresses. Not through sudden revelations, but through accumulating examples, refining models, discovering exceptions that force model improvements. 3I Atlas is a data point, a really interesting, potentially paradigm-shifting data point, but still fundamentally a data point in a larger dataset we're building one interstellar visitor at a time. The story doesn't end in January 2026 when the IAWN campaign concludes. That's just the end of the intensive observation phase. What comes after will be equally important in some ways. Data analysis, paper publication, scientific debate, consensus building or continued controversy, and most importantly, preparation for the next interstellar visitor and all the ones that follow. The data collected during the campaign will be analysed for months. Professional astronomers will be writing papers, submitting to peer-reviewed journals, presenting findings at conferences, the complete trajectory solution, incorporating all position measurements from all observers, the photometric light curve, showing how brightness varied over time, the spectroscopic results, cataloguing every detected emission line and what it tells us about composition, the physical characterization, estimating size, rotation, mass, structure based on all available evidence. Those papers will start appearing in early 2026. Some will focus on narrow technical questions. Did the centroid measurement techniques work as intended? How much did standardization improve data quality compared to previous observation campaigns? What systematic errors were identified, and how can they be corrected in future campaigns? Those might seem like dry methodological questions, but they matter for planetary defense readiness. Knowing your measurement systems are reliable is crucial when you need to trust those measurements during an actual threat scenario. Other papers will address bigger questions. What is 3I Atlas made of? How do we explain the nickel-to-iron ratio? What does the CO2-dominated composition tell us about its formation environment? Can we determine where in the galaxy it came from? How old is it really? Papers will propose models, test hypotheses, debate interpretations. That's the scientific process working as intended. Multiple researchers examining the same data from different perspectives, proposing competing explanations, seeing which models best fit observations, and some papers will be provocative. Loeb will almost certainly publish analysis arguing that the cumulative anomalies justify continued investigation of the artificial hypothesis. Other researchers will publish rebuttals arguing that natural explanations, while perhaps incomplete, are more scientifically parsimonious than invoking technology. The debate will be vigorous, sometimes contentious, ultimately productive because it forces both sides to sharpen their arguments and evidence. The JUICE data arrival in February 2026 will be a significant milestone. Those observations were made from a unique vantage point, capturing 3I Atlas in a highly active state that Earth-based telescopes couldn't fully observe. When JUICE's data is downlinked and processed, it might reveal features we've missed, confirm suspicions we've held, or introduce entirely new puzzles. It's a wild card, potentially answering questions or raising new ones we haven't thought to ask yet. The Juno encounter in March 2026, if it happens, would be historic regardless of outcome. The first spacecraft to closely observe an interstellar object. Direct imaging of the nucleus without atmospheric distortion. In situ measurements of gas composition and particle properties if Juno passes through the coma. Data quality orders of magnitude better than any telescope can provide. That would transform our understanding from educated inference to direct measurement. But Juno might not get redirected. The decision involves trade-offs, fuel costs, mission priorities, technical risks. NASA will weigh whether the scientific value justifies disrupting Juno's primary mission objectives. If the decision is no, that's not a failure. It's practical resource allocation. Juno was built for Jupiter, and ensuring it completes that mission successfully matters too. Longer term, 3I Atlas sets precedents for future encounters. The IAWN campaign structure proved that international coordination can mobilize quickly, that standardized protocols enable data integration, that combining professional and amateur observations creates robust data sets. Those lessons apply to the next interstellar visitor and all subsequent ones. Vera Rubin Observatory begins full operations in the coming years. It will revolutionize interstellar object detection. Its wide-field camera and rapid cadence, photographing the entire visible sky every few nights, will find objects earlier, track them longer, provide warning time that Oumuamua, Borisov, and 3I Atlas didn't allow. Instead of discovering visitors when they're already in the inner solar system or even leaving, we might detect them beyond Jupiter's orbit, giving months or years of observation time before perihelion. That changes everything. With earlier detection comes opportunity for spacecraft missions. The Comet Interceptor mission, currently being developed by the European Space Agency, is designed to wait in space until an interesting comet is detected, then launch an intercept trajectory, flying alongside the comet, studying it up close as it approaches the Sun. If Comet Interceptor is operational when the next interstellar visitor arrives, and if that visitor is detected early enough, we might intercept it. Humanity might send a probe to rendezvous with an object from another stellar system. Imagine that. A spacecraft built by humans flying alongside a comet billions of years old, formed around a star we can't even identify, capturing images of its nucleus, sampling its gases, measuring its magnetic field, watching it evolve in real time as solar heating activates its surface. That would be extraordinary. That would be first contact of a sort, not with life or intelligence necessarily, but with matter from elsewhere, physical material we can touch and analyze and understand. The search for extraterrestrial intelligence might increasingly focus on interstellar objects. If civilizations send probes rather than radio signals, if exploration is physical rather than electromagnetic, then detecting artificial objects among the natural ones becomes a legitimate SETI strategy. It requires looking for technological signatures, propulsion that can't be explained by gravity and outgassing, structural features suggesting construction, electromagnetic emissions inconsistent with thermal radiation, chemical compositions implying industrial processing. We're not equipped to do that systematically yet, but we could be. Future telescopes could be designed with technosignature detection in mind. Observation protocols could include searches for anomalous characteristics. Data analysis pipelines could flag objects exhibiting properties that warrant deeper investigation. It's not mainstream SETI yet, but it's gaining legitimacy as a complementary approach to traditional radio searches. 3I Atlas, regardless of what it ultimately proves to be, accelerates that conversation. It forces us to think seriously about how we would recognize an artificial object if one passed through. It highlights the gaps in our detection and characterization capabilities. It demonstrates that coordination is possible when motivation is sufficient, and it shows that public interest exists for these questions, that people care about understanding what's traveling through our cosmic neighborhood. One of the most remarkable aspects of the 3I Atlas campaign is the explicit invitation to citizen scientists. This marks a significant evolution in how planetary defense operates and how astronomical research incorporates non-professional contributors. Let's understand what this means and why it matters. Amateur astronomers have always contributed to comet discovery and observation. Many comets bear the names of their amateur discoverers. Backyard observers with modest equipment have found objects that professionals missed, documented unexpected outbursts, tracked faint visitors that would otherwise have gone unnoticed. That tradition is long-standing and well-respected in the astronomical community, but formal integration into planetary defense operations is different. The International Asteroid Warning Network is an official United Nations-endorsed system designed to protect Earth from cosmic impacts. It coordinates space agencies, national observatories, and institutional resources. Inviting amateurs into that structure, giving them official roles in a coordinated campaign, represents recognition that distributed observation networks have value beyond what centralized facilities can provide. The advantage is coverage. Professional observatories have limited telescope time. Competition for access is fierce. A major facility might dedicate a few hours per month to 3 hiatus observations, valuable hours but insufficient for continuous monitoring. Citizen scientists collectively can provide near-continuous coverage. Someone somewhere is observing almost any time the comet is above the horizon and weather permits. That temporal density of observations is impossible to achieve any other way. The geographic distribution matters too. Professional observatories cluster in certain locations: Chile, Hawaii, Arizona, the Canary Islands, Spain, a few dozen sites worldwide. But amateur astronomers exist everywhere: North America, Europe, Asia, Australia, South America, even Africa. When clouds cover Chile, someone in Australia might have clear skies. When an object is low on the horizon from Arizona, it might be perfectly placed for observation from Japan. Distributed networks have redundancy built in. The IAWN campaign leverages this. By standardizing methodologies through the mandatory workshop, they ensure amateur observations meet quality standards. By requiring registration, they know who's participating and can coordinate to fill observation gaps. By providing target ephemerides and observation priorities, they focus citizen scientist efforts on data most needed. It's organized amateur astronomy, harnessing enthusiasm and distributed resources for scientific purposes. For participants, the experience is extraordinary. You're not just photographing a pretty object, you're contributing to planetary defense readiness. Your measurements will be combined with data from Hubble, from Webb, from professional observatories worldwide. Your name will appear in the observation credits when papers are published. You're part of something larger than recreational stargazing. You're contributing to humanity's knowledge of an interstellar visitor that will never return. That sense of participation, of meaningful contribution, drives engagement. People who might casually observe occasionally become committed contributors, careful about their technique, meticulous about their data submission, proud of their role. That's the citizen science revolution. Not professionals generously allowing amateurs to watch from the sidelines, but genuine integration where contributions matter and participants know their work has value. The Unistellar network, a coordinated array of small, smart telescopes operated by citizen scientists, successfully detected 3I Atlas despite its faintness. Using image stacking techniques to compensate for rapid motion, even 3 to 4.5-inch aperture telescopes captured useful data. That's remarkable. Equipment that costs a few $1,000s, operated by amateurs in their backyards, contributing observations alongside facilities that cost hundreds of millions. Technology enables this. Modern cameras are sensitive, image processing software is sophisticated. Astrometry programs can extract precise positions from amateur images. Timing synchronization via GPS is standard. The quality gap between amateur and professional observations has narrowed dramatically. Not eliminated, professional facilities still have advantages in light-gathering power, instrumental stability, and atmospheric compensation. But narrowed enough that amateur data is scientifically useful when properly calibrated. The future of astronomy increasingly involves this hybrid model. Professionals for specialized high-difficulty observations requiring unique capabilities, amateurs for sustained monitoring providing temporal coverage and geographic redundancy, both contributing to shared databases, both following standardized protocols, both participating in collaborative science that neither could accomplish alone. 3's Atlas demonstrates this model working at scale for planetary defense. If it works here, it works for future interstellar visitors, for near-Earth asteroid monitoring, for comet tracking, for any scenario where sustained observation of moving targets is needed. That's a capability enhancement for humanity's space situational awareness. We're more capable of detecting and tracking cosmic visitors now than we were before this campaign began, and that capability will persist, strengthen, expand with each subsequent campaign. One concern that emerges in discussions of the IAWN campaign is transparency. Who sees the data? When does it become public? What mechanisms ensure findings are shared openly rather than restricted to inner circles? These are legitimate questions, especially when mandatory workshops and registration requirements create barriers to participation. In normal astronomical practice, observations are published rapidly. The Minor Planet Center issues electronic circulars, MPECs, announcing new discoveries and distributing updated orbital elements. Astronomers' telegrams share breaking observations of transient events. The ARXIV preprint server hosts papers before peer review, making research immediately available. This culture of openness enables rapid verification, independent analysis, and collaborative progress. But operational campaigns have different requirements. When hundreds of observers are submitting data, someone must coordinate, validate measurements, flag errors, integrate observations into coherent products. That coordination requires centralization. The Minor Planets Center serves this role for the 3 Aber Atlas campaign, receiving raw observations, checking them for consistency, updating orbital solutions, generating ephemerides for future observations. During the campaign, individual observations are published in MPEX as they arrive. Anyone can see what's being submitted, who's observing, what positions and brightnesses are being reported. That's transparent. But the aggregated analysis, the synthesis, combining all observations into comprehensive trajectory solutions and activity assessments, that happens internally at the Minor Planet Center. The full picture exists there, but isn't continuously broadcast. After the campaign, comprehensive results get published through peer-reviewed papers. Those papers contain detailed analysis, complete datasets often made available in supplementary materials, and findings that anyone can verify by examining the same data. That's eventually transparent. But there's a time lag. Months between observation and publication. During that period, campaign coordinators know things the public doesn't. Is that problematic? It depends on perspective. From an operational standpoint, it's necessary. You can't have effective coordination with complete decentralization. Someone must maintain the authoritative database, validate incoming data, generate products that observers use for continued observations. That requires temporary information asymmetry. From a transparency standpoint, it creates opportunities for selective disclosure. If coordinators wanted to withhold certain findings, the structure permits it. Most observations are public, but interpretations, particularly interpretations based on aggregating observations in ways outsiders can't replicate, could be restricted. Not saying this is happening, just acknowledging the possibility exists within the campaign structure. The remedy is community oversight. Multiple research groups have access to the same raw observations. Even if Minor Planet Center analysis remains internal temporarily, others can conduct independent analysis. Different researchers might reach different conclusions from the same data. That diversity of interpretation, that competition of ideas, provides a check against any single group controlling the narrative. Avi Loeb and the Galileo project represent this external oversight. They're analyzing 3-wire atlas independently, publishing findings through preprints and blog posts, reaching conclusions that sometimes differ from more conservative mainstream interpretations. That's healthy. That's science functioning properly. Multiple perspectives examining the same phenomenon, proposing different explanations, letting evidence arbitrate between competing hypotheses. The high-rise images from Mars Reconnaissance Orbiter represent a transparency challenge. Those observations were made in early October 2025. As of mid-November, they haven't been publicly released. NASA cites the government shutdown as causing delays. That's plausible. Shutdowns disrupt operations, delay data processing, postpone releases, but it's frustrating. Those images potentially contain the highest resolution view of 3I Atlas available from any source. Their continued unavailability feeds speculation about what they might show and why release is delayed. Congresswoman Anna Paulina Luna's intervention, working to get those images released, represents political accountability functioning. Elected representatives responding to constituent interest, applying pressure to agencies to ensure public data, becomes public promptly. That's how democratic systems provide oversight for scientific operations. If something is being inappropriately withheld, political pressure creates incentives for release. The broader lesson is that transparency is a process, not a state. Perfect real-time transparency is impossible for complex operations requiring coordination. But mechanisms for eventual transparency, for independent verification, for external oversight, these ensure that findings ultimately become public and that attempts to restrict information face obstacles from multiple directions. For 3I Atlas specifically, the scientific community is watching. Multiple research groups are involved. Different countries have observational assets pointed at the object. Independent citizen scientists are collecting their own data. That distributed observation network makes complete information control impractical. Too many eyes watching, too many independent datasets, too many people who would notice if official narratives contradicted what they're seeing. That's reassuring. Not because everyone trusts institutions automatically, but because the structure creates multiple independent verification paths. Transparency emerges from that redundancy even when individual components aren't perfectly transparent themselves. Despite months of intensive observations and unprecedented coordination, significant questions about 3I Atlas remain unanswered. Some will be resolved as the campaign continues and data analysis progresses. Others might remain mysterious long after the object vanishes from our view. Understanding what we don't know is as important as cataloguing what we do know. The size is still uncertain. The estimates range from 440 meters to 5.6 kilometers, more than a factor of 10 difference. That uncertainty comes from inability to separate the nucleus from the surrounding coma. We see the glow, we can't cleanly distinguish the solid body producing that glow. The high-RIC images from Mars Reconnaissance Orbiter, when released, might narrow this range. Juno, if it observes in March, could definitively measure size. But without those observations, we're working with informed estimates that span a huge range. The composition remains partially mysterious. We know it's CO2-rich water-poor emitting nickel and cyanide, but what else is present? Are there organic compounds we haven't detected yet? Are there volatiles sublimating at wavelengths we haven't observed? The James Webb Space Telescope detected CO2, water, and CO with its infrared spectrograph. But JWST's wavelength coverage isn't comprehensive. There might be signatures in ultraviolet or other spectral regions that haven't been adequately observed yet. The nickel without iron question has potential explanations but no confirmed solution. Is nickel tetracarbonyl really present, forming naturally in the comet's environment? Or is there another mechanism concentrating nickel while depleting iron? The observations show what's there, but not definitively how it got there. Multiple hypotheses remain plausible. Distinguishing between them requires more detailed spectroscopic analysis, ideally capturing the full emission spectrum at high resolution to identify subtle features that would diagnose specific chemical processes. The rotation period showed as 16.16 hours in July and August observations. But post-perihelion images in November show jets that should be smeared by rotation remaining tightly collimated. That's a puzzle. Either the rotation has changed, which seems physically unlikely over such short timescales, or the jets are somehow compensating for rotation in ways we don't understand, or there's another explanation we haven't considered. It's a minor mystery within the larger mystery, the kind of detail that seems like it should have a straightforward answer but doesn't yet. The origin remains speculative. We can trace 3I Atlas's trajectory back out of the solar system and determine the general direction it came from, near Sagittarius, toward the galactic center. But that doesn't identify a specific star system. The comet has been traveling for billions of years. Stars move. The stellar neighborhood that existed when 3I Atlas began its journey looks nothing like the current configuration. Determining where it actually formed would require detailed dynamical modeling, tracing stellar motions backward billions of years, searching for systems that were in the right position at the right time. That's possible in principle, but computationally intensive and uncertain. The age estimates range from 7 billion to possibly 14 billion years. That's constrained by velocity and trajectory. Objects moving faster have generally been travelling longer, but it's not definitive. The comet could have been gravitationally accelerated during close encounters with stars early in its journey, artificially increasing its velocity without corresponding increase in age. Or it could have formed in an unusually energetic environment where high velocities were common. We can estimate but not determine precisely. The fundamental nature remains an open question. Is 3I Atlas a natural comet formed through standard astrophysical processes in a different stellar environment? Or is there something genuinely unprecedented about it that resists incorporation into natural models? The spectrum of opinion ranges from definitely natural, just unusual, through probably natural but weird enough to warrant careful investigation, to anomalous enough that artificial hypothesis deserves consideration. Where any individual researcher falls on that spectrum depends on their prior assumptions, their tolerance for uncertainty, their assessment of how to weigh evidence when multiple explanations remain viable. Science thrives on unanswered questions. They drive investigation, motivate observation, stimulate theoretical work. 3I Atlas provides questions in abundance. Some will be answered through continued observation and analysis. Some will require future missions to similar objects. Some might remain permanently unresolved, limited by the one-time nature of the encounter and the constraints on our observational capabilities. That's frustrating but normal. Nature doesn't owe us complete answers. We work with what we can observe and measure, building understanding incrementally, accepting that some mysteries persist. Avi Loeb is comfortable with speculation. He proposes ideas that make many scientists uncomfortable. Artificial light sails explaining Oumuamua's acceleration, Trojan horse analogies for 3Y Atlas, suggestions that we should seriously consider extraterrestrial technology as an explanation when anomalies accumulate, that willingness to speculate publicly makes him controversial within his professional community, while making him popular with public audiences interested in possibilities beyond conventional thinking. Is speculation valuable or harmful? The answer depends on how it's done. Responsible speculation acknowledges uncertainty, presents multiple possibilities, avoids claiming certainty where evidence is insufficient. Irresponsible speculation asserts conclusions prematurely, cherry-picks data supporting preferred narratives, ignores alternative explanations. Loeb generally practices the former. He proposes hypotheses, he quantifies anomalies, he assigns probabilities based on cumulative evidence. He encourages investigation rather than demanding acceptance. The Loeb scale, ranking objects from 1 to 10 based on anomalous characteristics, represents structured speculation. It's not saying this is definitely artificial. It's saying here are observable anomalies, here are their individual probabilities, here's the cumulative assessment when you multiply those probabilities together, and here's where that places the object on a spectrum from definitely natural to worth investigating for technological signatures. That's defensible methodology. You can disagree with specific probability assignments. You can argue that some anomalies have natural explanations that haven't been fully explored yet. But the framework itself is reasonable. Speculation serves purposes even when wrong. It generates hypotheses that can be tested. It motivates observations that might not occur under more conservative approaches. It encourages thinking beyond established categories. If everyone assumed 3I Atlas was just another comet, certain measurements might not be prioritized. Searching for radio emissions wouldn't seem important. Looking for structural features suggesting manufacturing wouldn't be pursued. Conducting observations capable of distinguishing between natural and artificial scenarios wouldn't be designed. Loeb speculation ensures those observations happen. Whether or not 3I Atlas is artificial, the data collected while investigating that possibility has value. We learn more about the object than we would under conservative assumptions. We develop techniques that apply to future objects. We practice the observational and analytical methods that would be needed if we ever do encounter something genuinely artificial. The risk is that public speculation can confuse general audiences. Headlines report Harvard professor says comet might be alien spacecraft, without nuance about probability levels or alternative explanations. Social media amplifies sensational claims while ignoring careful caveats. People who don't follow the details might conclude there's stronger evidence for artificial origin than actually exists. That creates noise, makes serious discussion harder, gives ammunition to critics who dismiss any unconventional thinking as pseudoscience. Balancing those considerations is difficult. Scientists have responsibility to avoid misleading the public, but they also have responsibility to explore genuine possibilities even when those possibilities make colleagues uncomfortable. The solution, ideally, is careful communication, being clear about what's known versus speculated, being transparent about probability assessments and their limitations, being willing to say this is unlikely but worth investigating rather than either asserting confidence or refusing to discuss. Loeb isn't perfect at this balance. Sometimes his statements are more provocative than nuanced. Sometimes the framing emphasizes the unusual while understating the mundane. But he's operating in good faith, proposing testable hypotheses, conducting actual research rather than just pontificating. That distinguishes responsible speculation from irresponsible hype. The scientific community benefits from having people willing to explore unconventional ideas. Not everyone needs to do it. Most researchers should focus on incremental progress within established frameworks. That's where most discoveries come from. But having some individuals willing to ask uncomfortable questions, to propose hypotheses others find implausible, to investigate possibilities that conventional wisdom dismisses, that diversity of approach increases the probability that we notice genuinely unprecedented phenomena when they occur. If 3I Atlas turns out to be completely natural, explainable through processes we eventually understand better, Loeb will have been wrong about the technological hypothesis. That's fine. Science progresses through proposing and testing hypotheses, many of which turn out to be incorrect. If speculation motivated observations that improved our understanding of natural comets from other stellar systems, that's valuable even if the speculation itself was wrong. If 3I Atlas turns out to have characteristics that resist natural explanation and require considering artificial origins seriously, Loeb will have been vindicated in his willingness to ask the question. That's also fine. Science benefits from people who notice patterns others miss, who take anomalies seriously when others dismiss them, who investigate possibilities that seem unlikely but aren't impossible. Either way, speculation serves a function. It pushes boundaries, it challenges assumptions, it ensures we're not missing something important because it doesn't fit comfortable categories. 3I Atlas, regardless of its true nature, benefits from that intellectual diversity. We'll understand it better because multiple perspectives are examining it, proposing different explanations, conducting observations motivated by different hypotheses. That's how science should work. Beyond understanding 3I Atlas specifically, the campaign teaches lessons about planetary defense that will influence how we prepare for future scenarios. Some lessons are technical, some are organizational, some are about human psychology and international cooperation. All of them matter for ensuring we're ready when genuinely hazardous objects require response. Lesson 1. Early detection is everything. Oumuamua was discovered on its way out. Too late for detailed study, too late for spacecraft intercept, too late for anything except watching it leave. Borisov was discovered earlier but still not early enough for mission planning. 3I Atlas, despite being discovered in July, had limited pre-perihelion observation time because of its position near dense starfields, and later because of solar conjunction. We need detection systems that find objects farther out earlier in their approach, giving maximum time for observation and response if needed. Vera Rubin Observatory addresses this. Its wide field and rapid cadence will find objects beyond Jupiter's orbit, potentially providing years of warning instead of months. That transforms possibilities. Years allows spacecraft missions. Years allows thorough characterization without rushed, compromised observations. Years allows international coordination to function deliberately rather than frantically. The infrastructure investment in next-generation detection systems pays dividends many times over when it enables early awareness. Lesson 2. Standardization enables coordination. The IAWN campaign's mandatory workshop teaches standardized astrometry methods because without standardization, aggregating data from diverse sources produces garbage. Everyone measuring slightly differently, reporting in different formats, using incompatible coordinate systems that creates chaos that undermines coordination. Taking time to establish standards before observations begin pays off in data quality throughout the campaign. That lesson applies to any coordinated response requiring contributions from multiple organizations. Lesson 3. International cooperation is possible but requires structure. Observers from dozens of countries participating in the 3I Atlas campaign demonstrates that national boundaries don't prevent scientific collaboration, but it requires frameworks. The Minor Planet Center serves as neutral coordinator that everyone trusts. The IAWN provides endorsed protocols that legitimize the effort. The United Nations recommendation gives political backing. Without those structures, coordination would be much harder. Building and maintaining those frameworks during peacetime ensures they're available during crisis. Lesson 4. Transparency builds trust but requires balance. Complete real-time transparency is operationally impractical, but mechanisms for eventual transparency, for external verification, for independent analysis, these ensure that stakeholders can trust findings even when they can't see internal processes. Planetary defense requires public trust. Maintaining that trust requires demonstrating that findings are based on evidence, that multiple groups reach similar conclusions independently, that attempts to withhold or manipulate information face obstacles from multiple directions. Lesson 5. Citizen participation enhances capability and engagement. Professional resources alone can't provide the coverage that distributed networks offer. Integrating citizen scientists expands observational capacity while building public investment in the mission. People who contribute feel ownership. They become advocates. They understand challenges intimately. They explain to friends and family why this work matters. That social capital has value beyond pure data collection. It builds constituencies supporting continued funding and attention to planetary defense infrastructure. Lesson 6. Practice with real objects is more valuable than simulations. Drills and exercises have value. but nothing replaces observing actual targets under actual conditions with actual constraints. 3i Atlas provides experience that simulations can't fully replicate. The unexpected challenges, the limitations of actual equipment, the human factors of coordination across time zones and language barriers, the frustrations when weather interferes or equipment fails. All of that builds skills and resilience that transfer to genuine threat scenarios. Lesson 7. Uncertainty is uncomfortable but must be managed. Throughout the campaign, there's uncertainty about what 3IC Atlas is. That's uncomfortable. People want clear answers. But planetary defense scenarios will often involve uncertainty. Is this object hazardous? What's the impact probability? How big is it? What's it made of? Decision makers need frameworks for acting despite uncertainty, for managing risk when evidence is incomplete. Practicing uncertainty management with harmless objects builds capability for handling it when stakes are real. Lesson 8. Communication matters as much as technical capability. How findings are presented, how uncertainty is explained, how public questions are addressed. All of this influences whether people trust planetary defense systems. If communication is poor, if messages confuse rather than clarify, if scientists seem evasive or dismissive, trust erodes. 3i Atlas demonstrates both good and bad communication. NASA's straightforward factual statements work well. Sensationalized media coverage doesn't. Learning to communicate effectively under scrutiny is an essential skill. These lessons aren't revolutionary. They're common sense in many ways. But common sense needs to be practiced, internalized, demonstrated operationally. 3i Atlas provides that demonstration. When the next potential impactor is discovered, when planetary defense infrastructure must activate for real, the experience gained from this campaign will matter. The relationships built, the protocols tested, the lessons learned, all of that translates directly to improved readiness. So here we are, November 2025. The International Asteroid Warning Network campaign is active. Hundreds of observers worldwide are training their telescopes on 3i Atlas, measuring positions, monitoring brightness, documenting changes. The data accumulates. The picture gradually clarifies, and over the next 2 months we'll learn whether this interstellar visitor is a remarkably unusual natural comet or something else entirely. Beyond the technical questions, beyond the scientific uncertainties, 3i Atlas raises philosophical considerations about our place in the universe and how we relate to cosmic visitors from elsewhere. These aren't idle speculations. They're questions that influence how we approach future encounters and what we hope to learn from them. First, there's the question of uniqueness versus commonality. Is Earth special? Is our solar system unusual? Are the conditions that produced life here rare or common throughout the galaxy? Every interstellar visitor carries clues to these questions. Its composition reveals what materials were available in other stellar systems. Its chemistry shows what processes occurred during planetary system formation elsewhere. Its age tells us how long materials can survive in interstellar space without significant alteration. If 3i Atlas is typical of interstellar comets, if future visitors show similar characteristics, that suggests certain chemical processes are universal. CO2-rich, water-poor compositions might be common in outer regions of other planetary systems. Nickel emissions might occur frequently under conditions we're just beginning to understand. The universe might be more chemically diverse than we've assumed based on studying only our solar system. If 3i Atlas is anomalous even among interstellar visitors, if future objects don't show similar characteristics, that makes it even more interesting. It suggests either extraordinary formation conditions in its home system or processes affecting it during billions of years of interstellar travel that don't affect other objects. Either explanation expands our understanding of what's possible in the cosmic environment. Second, there's the question of detection and recognition. How good are we at identifying what's significant? If 3i Atlas is natural but our models don't fully explain it, are we missing natural phenomena that occur commonly elsewhere, but rarely enough in our solar system that we haven't recognized them? If it's artificial but we can't distinguish that from natural, how many previous visitors might we have misclassified? The history of science is filled with failures to recognize significance. X-rays were discovered by accident. Pulsars were initially thought to be instrument errors. The cosmic microwave background was dismissed as pigeon droppings. Scientists are human. They see what they expect to see. They explain observations through familiar frameworks. Genuinely unprecedented phenomena can be invisible even when data is available, simply because nobody thought to look for that specific thing or ask that particular question. 3i Atlas forces us to examine our assumptions. Are we adequately equipped to recognize technological artifacts if they pass through? Do our classification systems allow for possibilities beyond natural categories? Are we asking the right questions when analyzing data, or are we constraining ourselves to questions that fit within existing theoretical frameworks? These aren't easy questions. They challenge institutional inertia, scientific conservatism, and the practical reality that most research focuses on incremental progress within established paradigms rather than revolutionary paradigm shifts. Third, there's the question of contact and communication. If extraterrestrial intelligence exists, if civilizations send probes through space, would those probes attempt communication? Would they remain passive, observing without interacting? Would they be designed to be recognized if we're sufficiently advanced to notice them? These questions touch on the Fermi paradox, the apparent contradiction between high probability of extraterrestrial civilizations existing and the lack of evidence for their presence. One resolution to the Fermi paradox is that evidence exists, but we haven't recognized it. If artificial objects are designed to appear natural, if they avoid obvious signatures while conducting observations, we might encounter them regularly without realizing what we're seeing. That's the Trojan horse scenario Loeb invokes, not claiming 3i Atlas is artificial, but asking whether our detection and classification methods are sophisticated enough to distinguish between natural and artificial if the artificial is deliberately camouflaged. Another resolution is the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact with developing species to allow natural evolution without interference. If that's true, probes might observe passively without attempting interaction, making detection difficult unless we specifically search for subtle indicators of technological origin. 3i Atlas's trajectory, bringing it through the inner solar system where planets reside while avoiding close approaches to any of them, could be consistent with passive observation designed to minimize disturbance. These aren't mainstream scientific positions. Most researchers consider them speculative at best, but they're philosophically coherent possibilities that deserve consideration in contexts like 3i Atlas, where anomalous characteristics resist easy, natural explanation. Not claiming they're true, but acknowledging they exist as possibilities within the space of logically consistent hypotheses about reality. Fourth, there's the question of existential significance. Does it matter whether 3i Atlas is natural or artificial? Beyond scientific curiosity, beyond technical questions, does the answer have implications for how we understand ourselves and our place in the cosmos? If it's natural, that's fascinating scientifically, but doesn't fundamentally change our existential situation. We're alone, or at least not yet in contact with others. The universe contains remarkable natural processes producing complex chemistry and diverse structures through purely physical mechanisms. We continue our exploration, our search, our slow accumulation of knowledge about the cosmos we inhabit, without the shock of contact with alien intelligence. If it's artificial, that changes everything, immediately and profoundly. It means we're not alone. It means intelligence exists or has existed elsewhere. It means the universe contains or contained minds other than ours, thoughts other than human thoughts, perspectives shaped by evolutionary histories completely different from our own. It means the possibility of communication, of learning from civilizations potentially far more advanced than ours, of accessing knowledge we couldn't develop independently. That would be the most significant discovery in human history, not hyperbole. Genuinely the most important revelation possible. It would reframe every question about our place in the universe, our significance, our future, our potential. It would challenge religions, philosophies, political structures, all built on implicit assumptions about human uniqueness or centrality. It would inspire some and terrify others. It would unite some in recognition of common humanity while dividing others over how to respond. So yes, the answer matters, enormously, which is why caution is appropriate. Extraordinary claims require extraordinary evidence. The possibility of being wrong, of misinterpreting natural phenomena as artificial, carries consequences. Announcing artificial origin prematurely would damage credibility, undermine trust in scientific institutions, and make genuine discoveries less believable later. Better to be methodical, thorough, conservative in interpretation, while remaining open to evidence wherever it leads. Step back. Look at 3I Atlas not as an isolated curiosity, but as one example of what's constantly happening in the galaxy. Matter flows between stellar systems. Comets are ejected through gravitational interactions. Planetary collisions scatter debris. Material escapes constantly, mixing compositions, distributing elements, creating the cosmic ecology where stellar systems aren't isolated but connected through exchange of physical matter over billions of years. Our solar system participates in this exchange. We eject comets into interstellar space. Gravitational interactions with Jupiter and other planets send long-period comets onto hyperbolic trajectories, leaving the solar system permanently. Calculations suggest we've ejected trillions of comets over 4.6 billion years. Those objects are now scattered throughout the galaxy, some perhaps passing through other stellar systems just as 3Y Atlas passes through ours. If we send, we receive. The flow is bidirectional. Interstellar visitors arrive constantly. We've detected 3. How many have we missed? How many are too small to see? How many passed through before we had telescopes capable of detecting them? The 3 confirmed interstellar objects represent the tip of an iceberg, visible examples of a phenomenon that's ongoing and ubiquitous. This cosmic ecology has implications for life. If organic molecules are common in interstellar objects, if life's chemical precursors are distributed throughout the galaxy through these exchanges, then abiogenesis, the origin of life, might benefit from pre-existing organic chemistry rather than starting from purely inorganic materials. Panspermia, the theory that life or its precursors spread between stellar systems through physical transport, becomes more plausible when we recognize the volume of material flowing through interstellar space. We haven't detected organic molecules in 3I Atlas definitively yet. Cyanide is present, a simple organic compound, but complex organics, amino acids, nucleotides, lipids, the building blocks of life as we know it, those haven't been confirmed. Future observations might detect them, or might not. The data will tell us what's there. But the possibility that interstellar comets carry organic chemistry reinforces the idea that life's ingredients aren't unique to Earth, that the raw materials exist throughout the galaxy distributed by natural processes. This perspective also contextualizes the search for extraterrestrial intelligence. If billions of comets flow through space, if stellar systems constantly exchange material, then sending intentional messages through physical objects becomes feasible, not efficient for communication. Light-speed electromagnetic signals are faster, but feasible for long-term archival, for sending information that persists over millions of years, for creating a distributed library accessible to any civilization that develops spacefaring capability. Imagine encoding information in an artificial comet structure or composition. Not shouting we're here, but quietly leaving messages that sufficiently advanced civilizations would recognize. That requires no faster-than-light travel, no violation of physics, just patience and willingness to think on timescales of millions of years. If you're a civilization planning for deep future, that approach has elegance. You let your messages drift, intersecting stellar systems probabilistically, creating opportunities for discovery that persist long after your own civilization might have ended. This is speculation, pure speculation. But it's grounded speculation, based on known physics consistent with observed phenomena, requiring no exotic assumptions beyond the existence of intelligence elsewhere, at some point in galactic history. Whether 3I Atlas represents such a message, we don't know. Probably not. Probably it's a natural comet, but the framework exists, the method is physically possible, and if we're thinking about how to search for extraterrestrial intelligence comprehensively, considering physical artifacts alongside electromagnetic signals makes sense. The cosmic perspective also humbles us. 3 Atlas is ancient, billions of years old, formed around a star that might not exist anymore. It's been travelling through space longer than Earth has existed. It's seen more of the galaxy than humanity ever will unless we develop interstellar travel capabilities we don't currently possess. It's a cosmic elder, a traveller whose journey spans epochs we can barely comprehend. What has it experienced during that journey? Close encounters with other stars, passage through molecular clouds, bombardment by cosmic rays gradually altering its surface chemistry? We can infer some of this through theoretical models and observations, but imagination fills gaps that data can't resolve. This object has a history, a narrative written in chemistry and trajectory that we're trying to read from momentary glimpses as it passes through our neighbourhood. And when it leaves, it continues. Its journey doesn't end when it exits our solar system. It travels onward through the galaxy, potentially for billions more years, potentially encountering other stellar systems, other planets, possibly other civilizations. What we learn about it becomes part of a larger story that extends far beyond our observation window. We're one brief chapter in a narrative that spans galactic timescales. That perspective makes our observations precious. We have one chance, 2 months of optimal visibility, then it's gone beyond reach, continuing its journey through a galaxy we'll never fully explore. What we learn now contributes to human knowledge permanently. The data collected during these weeks will be analysed for years, mined for insights, referenced by researchers studying future interstellar visitors. It's a foundation for understanding phenomena we're only beginning to recognise. Let's be clear about what we know and what we don't. We know 3I Atlas is real, interstellar, moving through our solar system. We know it exhibits characteristics that don't perfectly match standard comet models. We know it's triggered unprecedented coordination through the IAWN campaign. All of that is factual, verified, documented. We don't know why these characteristics occur together. We don't know whether natural explanations will ultimately explain everything or whether some aspects remain genuinely puzzling even after thorough investigation. We don't know what the December observations will reveal or what the JUICE data will show in February. We don't know what papers will conclude when they're published next year. Uncertainty dominates, and that's okay. That's normal. That's science working as intended. What we do with that uncertainty matters. Responsible engagement means acknowledging what we don't know while clearly stating what we do know. It means considering multiple hypotheses without prematurely favouring one. It means following evidence without dismissing possibilities because they seem unlikely. It means participating in the conversation, asking questions, contributing observations if we're able, sharing information accurately when communicating with others. For viewers of this video, for members of the Sleepy Explorer community, engagement means staying informed. The campaign continues through January, developments will emerge, data will be released, findings will be published. Following along requires commitment, not obsessive attention but sustained interest, checking in periodically, reading updates, thinking critically about what's being reported. It means distinguishing signal from noise. Media loves sensational headlines. Social media amplifies dramatic claims. Some coverage of 3I Atlas is accurate and measured. Some is exaggerated or misleading. Developing ability to distinguish requires practice, attention to sources, verification through multiple independent reports. That's media literacy, increasingly essential skill in information-saturated environments. It means accepting uncertainty without demanding premature closure. We want answers. Human psychology craves resolution. But rushing to conclusions before evidence justifies them is worse than maintaining uncertainty. Better to say we don't know yet than to commit to explanations that later prove wrong. That intellectual humility, that comfort with ambiguity, that willingness to wait for data, these are marks of mature thinking. It means engaging respectfully with people who reach different conclusions. Some will be convinced 3I Atlas is completely natural. Some will think the anomalies suggest something more interesting. Some will be skeptical of official narratives, some will trust institutional science completely. All those positions are held by reasonable people responding to the same data, with different prior assumptions and interpretive frameworks. Disagreement is healthy, contempt is not. We can argue about evidence while respecting people, and it means recognizing significance beyond immediate explanations. Whether 3I Atlas turns out to be natural or artificial, completely understood or permanently mysterious, the campaign demonstrates humanity's capability to coordinate when motivated. The observations we're collecting advance our understanding of the galaxy. The infrastructure being tested improves our planetary defense readiness. The public engagement builds investment in space science and cosmic awareness. All of that has value independent of what 3I Atlas ultimately proves to be. So here's what I'm asking. Subscribe to this channel, hit that button, because I'll be covering every development as the campaign continues. Workshop details if they emerge, observation findings as they're published, spectroscopic updates, December approach coverage, JUICE data in February, Juno encounter in March, campaign conclusions in late January. This is ongoing coverage of an ongoing story, and staying subscribed means you're informed as events unfold. hit the notification bell. Turn on all notifications, because timing matters with breaking developments. You want to know when significant findings are announced, when papers are published, when spacecraft observations are released. Immediate notification means you're part of the conversation while it's happening, not catching up days later after initial discussions conclude. Comment below. Tell me your thoughts. Where do you stand on 3i Atlas? Natural comet with unusual chemistry? Something more puzzling? What questions do you want answered? What observations do you think are most important? Your perspective matters. This community includes knowledgeable observers, curious learners, skeptical questioners, all contributing to shared understanding. Your voice adds to that collective intelligence. And tell me where you're watching from. This is a global story involving international coordination, observations from every continent, people worldwide paying attention. I want to see that geographic distribution. Where is this community located? How far does interest reach? Comment with your location. Let's see how planetary this conversation actually is. Share this video if it resonated with you. If the questions feel important, if you think others should understand what's happening with 3i Atlas, share it. Reddit communities focused on space and astronomy. Twitter threads discussing the comet. Facebook groups interested in cosmic phenomena. Discord servers where science enthusiasts gather. Wherever your networks exist, sharing helps expand awareness. Because here's the thing, this story matters beyond any individual object. It matters because it's teaching us how to function as a space-aware civilization, how to detect visitors, how to coordinate observations, how to distinguish normal from anomalous, how to respond to uncertainty, how to engage public interest while maintaining scientific rigor. These are capabilities we'll need for the future we're building, where space isn't distant abstraction but proximate reality we interact with constantly. 3i Atlas is one visitor among billions that will flow through the solar system over coming millennia. It's special because it's happening now, during our lifetimes, with technology sufficient for detailed study. But it's also representative of what's always occurring, what's been occurring for billions of years, what will continue occurring long after human civilization ends or transforms into something we can't currently imagine. We're learning to notice. That's the fundamental lesson. Learning to detect, to characterize, to study, to understand visitors from elsewhere in the galaxy. That capacity, that skill set, that institutional infrastructure, it's being built now, refined through campaigns like this. Improved with each subsequent detection. By the time Vera Rubin Observatory finds dozens or hundreds of interstellar objects, we'll have frameworks for rapid assessment, criteria for determining which merit intensive study, protocols for mobilizing resources efficiently. That readiness is built through experience, through practice, through occasions like this, where we test our systems with real objects under real conditions. And maybe, just maybe, we're learning to recognize something more. Maybe 3i Atlas is completely natural and teaches us about stellar chemistry elsewhere in the galaxy. Maybe it's something more remarkable and teaches us we're not alone in the cosmos. Either way, we're expanding our awareness, our capability, our understanding. That expansion is valuable in itself, independent of any specific discovery. So watch this space, literally. Watch 3i Atlas over the coming weeks. Follow the observations, read the papers, think about the implications, and recognize you're witnessing history, not ancient history we study from comfortable temporal distance. History being made now, in real time, with outcomes undetermined, with questions unanswered, with possibilities still open. That's rare, that's special, that's worth paying attention to. December 19th, 2025. The closest approach. A billion-year-old traveller and a young civilization briefly crossing paths in the cosmic night. What we learn from that encounter shapes our understanding and our future in ways we're only beginning to appreciate. Stay curious, stay engaged, stay watching, and I'll see you in the next update as this remarkable story continues to unfold. Thanks for watching, and remember to look up, because the universe is out there, vast and ancient and full of mysteries we're only beginning to explore. 3i Atlas is one of those mysteries, and we're fortunate enough to be alive at the moment when it passes through our neighbourhood, giving us this extraordinary opportunity to study something from elsewhere, something that connects us to the wider galaxy we inhabit. This is the Sleepy Explorer, reminding you that the cosmos never sleeps, and neither should our curiosity about it. Until next time, let's be clear about what we know and what we don't. We know 3i Atlas is real, interstellar, moving through our solar system on a hyperbolic trajectory. We know it exhibits chemical characteristics that don't match standard comet models: nickel without iron, CO2-dominated composition, anti-tail features, aligned trajectory, high velocity, substantial size, blue color at perihelion, each observation documented, each anomaly verified through multiple independent sources. We don't know why these characteristics occur together in this object. We don't know why the trajectory aligns with our planetary plane. We don't know what the mandatory workshop teaches or what campaign coordinators see in the aggregated data. We don't know what JUICE observed or what the HiRISE images show. We don't know what will happen when Juno gets close in March 2026. We don't know if 3I Atlas is the strangest natural comet we've encountered, or the first artificial object we've detected without recognizing it. Multiple interpretations remain valid. If you believe this is responsible planetary defense training using a convenient interstellar visitor to validate systems, you're supported by substantial evidence. The campaign structure, the stated objectives, the training emphasis, all align with legitimate preparedness exercises. That's reasonable and well-grounded. If you believe something more significant is occurring, that the anomalies warrant investigation beyond routine training, that the unprecedented response indicates genuine uncertainty about what 3I Atlas represents, you're also supported by evidence. The chemical inconsistencies, the unusual mobilization, the tight timelines, the restricted participation, all suggest priorities beyond typical training. That's equally reasonable and equally grounded. Both can be true simultaneously. Training that uses real anomalous data becomes investigation when the training target exhibits characteristics demanding serious study. The categories aren't mutually exclusive. What makes this moment special is timing. This isn't historical analysis of events long past. This is happening now, right now. The campaign is active. Observations are ongoing. Between now and January 27th, 2026, we'll have answers, or at least more data. 3I Atlas won't remain mysterious indefinitely. Either observations resolve anomalies through natural explanations, or they deepen mysteries further. Either way, we'll know more in 2 months than we know today. That's why you need to stay engaged. If this story resonates with you, if the questions we've raised feel significant, if you think understanding what's really happening with 3I Atlas matters, then follow along. The campaign continues through January. Data will emerge throughout December. Findings will be published in early 2026, and the implications, whatever they turn out to be, will shape how we think about our place in the universe. Look, I'll be covering every significant development. Workshop details if they leak, observation findings as they're published, spectroscopic updates, JUICE data when it arrives in February, Juno encounter in March if it happens, campaign conclusions and analysis when the official observation window closes. This is ongoing, this is active, and I'm committed to tracking it through completion. So hit that subscribe button right now if you haven't already. Because this is a continuing story and timing matters. When findings emerge, they'll be newsworthy for days before mainstream coverage moves on. Being subscribed means you're informed while discussion is active, while you can participate, while your engagement helps keep attention focused. Hit the notification bell, seriously, because I'll be publishing updates as developments happen, and you want to see them immediately, not 3 days later when the algorithm decides to show you the video. Drop a comment. Tell me your thoughts. Based on everything you've heard, do you think 3I Atlas is a natural comet with unusual but explainable characteristics? Or do you think something more significant is happening here? Don't just lurk. Your perspective matters. This is a global conversation involving observers on every continent. Researchers from dozens of countries. Your voice contributes to that conversation. And tell me where you're watching from, because this campaign involves international participation, observatories worldwide, and I want to see how far this community reaches. Are you in North America, Europe, Asia, South America, Australia, Africa? Where are you paying attention from? Share this video if it feels significant, if the questions resonate, if you think others should know what's happening with 3I Atlas and the IAWN campaign. Use whatever platform you prefer, Reddit, Twitter, Facebook, Discord, wherever your communities gather. Because the more people watching, the more pressure for transparency. The more questions asked, the harder it becomes for inconvenient findings to disappear into data embargoes or get filed away without proper investigation. You're not passive observers. By watching this, by engaging critically, by refusing to accept surface explanations without scrutiny, you're contributing to oversight. Science functions best with public attention. Transparency emerges when people care enough to demand it. Your attention isn't incidental, it's essential. 3I Atlas is out there right now, moving away from us at 210,000 kilometers per hour. Every hour it travels another 210,000 kilometers deeper into space. Every day another 5 million kilometers. By the time you finish watching this, it's measurably farther from us than when you started. This object is leaving. Everything we're going to learn will be learned while it's still observable, or it won't be learned at all. The campaign launches November 27th. Coordinated observations begin. Data accumulation starts. 2 months of intensive study. 2 months to characterize this visitor. 2 months to determine whether it's just another comet passing through, or whether it's the beginning of understanding that the universe contains surprises we're only now equipped to recognize. Stay curious, stay skeptical, stay engaged. And whatever happens over these next 90 days, remember you were paying attention when it mattered, when knowledge was being created, when answers were uncertain, when asking questions was more important than pretending to have definitive explanations. The campaign is active, the observations are starting. History is being written in real time, and we're watching it happen. Thanks for watching. I'll see you in the next update.